very thing was the following, and I will come to this. First of all, we had to work with normalized data. In fact, it is not necessary because you see we can work also with initial data without any normalization, but with normalization sometimes it's more comfortable, and these are one of the ways to study normalization. And the model which I introduced, it was the model in which instead of using this initial data, even in the normalized form, we switch to the vectors of the dimension less than 1 for comparing with the dimension of initial data by moving to the evaluation of tangencies of the angles of each piece of the curve. Okay. And then this very work was used in many fields. We have many publications on this, including one publication with Boris in the journal in Russian. But then we confront with the following problem, which was really very serious situation, which we first time when I worked with big data, when it was necessary to do it with millions of the curves of this kind, which were these curves presented the consumer behavior of the very big retail network. I cannot tell about this openly because it is, I signed NDA agreement, but it was in Europe and we had millions of these very curves. Here it is written index 1, index 2, but these are, for instance, goods. And follows. You see, again, we consider these very parameters are not the values. And consider that then you see for small values it will be rather small, tube will be smaller. For higher values it will be greater. There are many other ways to define these epsilon tubes, and we might work on this. And then after we define these epsilon tubes, we can look at this very case. For instance, this very indices evaluate some parameters of the object. And you see with this very epsilon being 5%, we have here four curves inside these epsilon tubes, and we can derive that these very objects with this very curves might be considered as very similar. You see. And important part of this story is the following. You see, when we analyze these millions of curves for this real retail network consumer baskets, I remember very well, you see, when I proposed several models how to do it rather fast, my colleagues who were working on this software said to me that please don't propose any kind of algorithm which is not linear, because you see it will not work properly. And as you can see, this very model, this very kind of approach is linear, and so we can process enormous, and we did it, enormously high samples of objects. Now I go to some kind of, if you don't have questions here, I will go to some applications. And first of all, we did some work, and we work on this permanently. You see, it is very, very good, let's say, apparatus, very good. We have a software, and we work on this a lot. For instance, analysis of economic indicators of regions of Russia. And here are, I don't remember, did I? No, I didn't include it. So we have here, for instance, gross domestic product, unemployment, average salary, etc., for regions, and we can construct this kind of curves and consider how they work together, how they are, to which extent they are similar. Yes, and there are many different tasks which we work on this way. First of all, naturally, collect tasks, collect data, then pre-processing, then cluster region. And what is important, you can see the usual way how we work with this very data, but what is important now, we might consider, we might we have here some kind of, you see, different applied problems to work on this. For instance, in agriculture, to consider production of animal products, industrial production index, investments of fixed assets. We did it in many for the banks, not only in Russia, also in other countries. We did it for, we didn't write it here, but we did it for behavior of parties in different countries, for instance, Britain, Finland, Russia, naturally, European Union, South America, Africa, etc. Then you can see here retail turnover, wholesale turnover, and many other applications. But what is interesting is that we extended it also and applied it. I think that the first application of it, first publication, was in the beginning of 2000s when we applied it to the main parameters, macroeconomic parameters of the countries. And we published an article with my colleague from Turkey, who was macroeconomist, in Japanese Economic Review, where we consider it for countries for some period, all these important macroeconomic parameters, and then we did this kind of, let's say, I call it dynamic pattern analysis. And what was interesting is that the idea now was the following. You see, first we cluster these countries and put them into different groups in different years, and then we consider how they change this very trajectory over years, how they switch clusters or patterns, static patterns, over years. And it was very interesting. There were very interesting results when we did it for banks, for instance, for Turkish banks. We did it first time, and it was interesting that out of several hundred, maybe less than, no, not several hundred, but several, these banks, maybe about 60 or 90, I don't remember exactly. What was interesting, there were rather very interesting and very well-behaved groups, banks in some groups, but in one group, nobody could explain why they change these clusters so frequently, etc. And their behavior over years, over months even, you see, we did it. And what was interesting that it was about 21, I think, banks in 22 maybe banks in one group. And then it was very interesting that when in 1 year and a half there was a crisis, 18 banks from this very group just crashed, you see. Other banks from other groups were okay, but this very group where we very strong scientists in finance could not explain what is going on with this group, they crashed. Okay, so I stop here. I talked 20 minutes and I am ready to respond to the questions. Thank you. There are some kind of publications. These are in Japanese Economic Review. So there were several publications in concerning Russian banks, and there was a explanation of pattern analysis in statics and dynamics with Boris Mirkin. And again, I would like to say my thanks to Boris, who first attracted my attention. Nobody did it before. I told this very model, presented this very model in several conferences on data analysis several times. Nobody told me that it is in fact related to the clustering in parallel coordinates. Okay, thank you very much. My response to the what is y-axis is the value of the parameter. In the x-axis is just the name of the parameter. In the y-axis is the value of the parameter.
I wrote 2 questions if you can see.
This is a very good question. Epsilon, we usually do it in for several epsilons and look of the pictures, how they correspond to each other. It is very easy, you see, because you see we have these pictures just in the on the plane, so we can understand how it works. And that's why, by the way, we construct this very man-machine procedure. You see, we always can compare this with our with the representation on the plane of these curves.
I will speak Russian. Во-первых, с днем рождения, Борис Григорьевич. Борис Григорьевич, как известно, имеет разнообразные научные интересы, но вот, так сказать, на мой взгляд, может, я ошибаюсь, меня поправят, что, конечно, основные вот интересы сосредоточены вокруг кластеризации, поэтому я буду говорить сейчас исключительно о кластеризации. И здесь, конечно, наверное, трудно чем-то удивить новым Бориса Григорьевича, поскольку, ну вот я обычно студентам своим говорю, что когда там возникает какой-то вопрос сложный, связанный с кластеризацией, я говорю, у вас есть уникальная возможность получить консультацию с первых уст от человека, который знает про кластеры все, и направляю их к вам, да. Я не знаю, доходят ли они до вас, но я так делаю. Не доходят. Не доходят. Да, ну вот так. Ну и поэтому вот удивить как бы нечем тут в этом плане, но я так думаю. Но можно удивить вот именно объектами кластеризации. Что кластеризовать? Вот в этом смысле я хочу вот сейчас как раз рассказать о кластеризации таких объектов, которые называются телами свидетельств. в рамках вот теории Демпстера-Шеффера рассматриваются такие объекты, которые называются телами свидетельств. Они имеют такую сложную структуру. Во-первых, это такие пары, состоящие из наборов подмножеств некоторого множества и связанных с ними функциями масс. Сами подмножества характеризуют степень уверенности, что вот, характеризуют, вернее, то множество, которому может принадлежать истинная альтернатива, а массы, частоты характеризуют степень уверенности, что вот истинная альтернатива принадлежит тому или иному множеству. Вот эти тела свидетельств, они могут иметь довольно сложную структуру. Да, сами вот эти подмножества называют фокальными элементами, они могут иметь довольно сложную структуру, могут пересекаться, могут вкладываться, могут не пересекаться и так далее, и так далее. И таких фокальных элементов может быть довольно много вот, в реальных телах свидетельств. Поэтому требуется их кластеризовать для того, чтобы решать, ну, во-первых, задачу аппроксимации, когда мы заменяем тело свидетельств вот из множества фокальных элементов, заменим более простым телом свидетельств, состоящих из нескольких фокальных элементов, но тем не менее, чтобы вот какая-то мера близости между этими объектами выполнялась. Во-вторых, вычислительная сложность. Значит, вот основные вычисления там связаны, они носят такой экспоненциальный характер, поэтому чем меньше там тел свидетельств, тем вычислительная сложность вот этих алгоритмов будет, связанных с обработкой таких объектов, будет выше. Это что касается вот мотивации исследований. Ну, я пару слов скажу вот о самой этой теории Демпстера-Шеффера, в рамках которой рассматриваются вот эти объекты, тела свидетельств. Значит, это довольно уже такая старая теория, берет свое начало от двух таких работ пионерских, Демпстера 1967 года и Шаффера 1976 года. Демпстер такой статистик, чистый статистик из Гарварда, сейчас очень он такого преклонного возраста, но за 90, но вот недавно я даже видел его работу какую-то совсем свежую. А Шаффер помоложе, значительно моложе, и имеет такие разнообразные, в общем-то, интересы. И вот в это время он был совсем молодым человеком, когда написал эту монографию. Он как раз занимался развитием этой теории. И эта монография, кстати, не потеряла актуальность даже и в настоящее время. Так вот, основные тут моменты такие, что рассматривается некоторое множество, универсальное множество, как обычно, x, и на нем рассматривается какое-то конечное подмножество этого множества. Называют эти подмножества фокальными элементами. Вот так будем обозначать скрипт. С этими подмножествами связана функция масс. Функция масс – это вот не отрицательная функция, а удовлетворяющая условия нормировки, что сумма всех масс равна единице. Вот такая как раз пара из множества фокальных элементов и функции массы называется телом свидетельств. Да, ну считается, что для каждого фокального элемента масса не нулевая. Значит, простейшим телом свидетельства является такое категоричное, как говорят, тело свидетельств, состоящее всего из одного фокального элемента с единичной массой. Ну и можно сказать так, что любое тело свидетельств можно представить в виде вот такой выпуклой комбинации категоричных тел свидетельств с коэффициентами, равными массам. Ну вот чуть посложнее, чем категоричное тело свидетельств. Это вот такое свидетельство называется простое. Когда с каким-то коэффициентом мы берем категоричное тело свидетельств, построенное на каком-то фокальном элементе, а всю остальную массу относим к всему универсальному множеству x. Вот эта часть, второе слагаемое, она характеризует как бы степень нашего незнания о принадлежности истинной альтернативы множеству а, степень нашего незнания. Значит, с телом свидетельств связывают несколько таких функций множеств. Но самые популярные из них это функция доверия, функция правдоподобия, которая вот так строится, и которая являются нижними и верхними оценками вероятности события того, что истинная альтернатива принадлежит множеству А. Значит, вот с такой графовой точки зрения тело свидетельств можно считать вот гиперграфом. Вчера как раз этот термин уже вспоминался на конференции. Можно считать, что это есть такой гиперграф, когда у нас, значит, элементы множества X это вершины этого гиперграфа, а гипердуги это как раз вот эти фокальные элементы. Ну, вот пример приведен. Вот так можно в строчку это записать, как выпуклую комбинацию категоричных тел свидетельств, построенных на фокальных элементах. Вот здесь внизу фокальные элементы как раз перечислены нашего тела свидетельств. Это масса их. А это вот такое гиперграфовое представление этого тела свидетельств. Так вот, такие объекты надо кластеризовать. Значит, что кластеризовать? Ну, кластеризовать, конечно, в первую очередь нужно вот эти фокальные элементы, но с учетом их масс, конечно. Да, что если там какой-то фокальный элемент имеет маленькую массу, то он может быть для нас не такой и важный. А если там большая масса, то это более важные такие фокальные элементы. С учетом масс, конечно. Причем вот здесь при кластеризации часто как бы метрические характеристики, они не важны. Не столь важны метрические характеристики, сколь важны характеристики, ну, связанные вот с понятием конфликта между фокальными элементами, между телами свидетельств, конфликта, либо противоречия. Ну, вот что можно считать конфликтными, неконфликтными фокальными элементами? Если сильно как бы пересекаются, вот, грубо говоря, сильно пересекаются два фокальных элемента, то вот такую пару можно назвать парой неконфликтных фокальных элементов, поскольку истинная альтернатива, вот один источник, например, говорит, принадлежит множеству А, второе множеству Б, ну, эти множества довольно близкие, и в этом случае вот эти свидетельства от этих источников, они действительно как бы воспринимаются неконфликтно. Если они слабенько пересекаются, то вот здесь уже есть какой-то слабый конфликт. Если они вообще не пересекаются, то здесь уже есть такой сильный конфликт между этими фокальными элементами и соответствующими свидетельствами. Если у нас вот есть тела свидетельств из множества таких вот пар построенных, множество фокальных элементов, то можно по-разному мерить конфликт. Но вот такая билинейная форма, самая популярная для измерения конфликта, сумма произведений масс фокальных элементов, которая берется по парам фокальных элементов, которые между собой не пересекаются. То есть тут учитывается только вот третья ситуация, конфликтность. Средняя не учитывается, хотя можно ее учитывать. Вот здесь нужно просто оставить какой-то коэффициент в меру пересечения, там типа индекса Джакара там, или еще что-нибудь. И тогда можно и учитывать и слабую ситуацию. Но не суть, не в этом суть. Значит, вот что касается кластеризации, то тут есть несколько подходов, значит, которые я сейчас коротко охарактеризую. Значит, первый подход – это такая иерархическая кластеризация. Она была предложена вот лет 20 назад Дено, Тьерри Дено, и в некоторых еще работах она встречалась, и даже более ранняя работа есть, и позже развивалась. Это такая вот, как мы сказали, агломеративная иерархическая кластеризация. В этом случае строится два тела свидетельств. Тело внутренней как бы кластеризации и внешней кластеризации. Строится так. Это берутся, да, вот обозначены они F-, F+. Тело внутренней кластеризации, внешней кластеризации. Значит, тело свидетельств внутренней кластеризации строится на пересечении множеств, некоторых множеств из из исходного множества фокальных элементов, а тело свидетельств внешней кластеризации на их объединение. При этом и в том, и в другом случае массы суммируются. Массы просто суммируются. Значит, какие пары выбирать для пересечений и для объединений, но решается по-разному. Ну, например, можно построить, использовать вот такой, например, функционал неточности тела свидетельств. Значит, чем больше у нас тел свидетельств больших по мощности с большими массами, тем более неточное у нас это свидетельство. Так вот, можно выбирать такие пары, которые при объединении либо при пересечении мало меняют вот этот функционал неточности. То есть в этом случае можно ожидать, что какая-то мера близости у нас будет выполняться мера близости между тем, что мы получим в результате этой иерархической кластеризации и исходным телом свидетельств. Но вот если расписать для пар этот функционал, то он при объединении пар примет такой вид, а при пересечении такой вид. Ну и тогда, соответственно, выбираются те пары для внутренней кластеризации, которые минимизируют этот функционал, для внешней, которые минимизируют этот функционал. Ну вот на том же примере, вот, который там был у нас, вот он в серединочке, тело свидетельств, в результате применения вот этой внешней и внутренней кластеризации мы получим вот такие результаты. Вот будет такая внутренняя кластеризация и вот такая внешняя кластеризация. То есть в этом случае тут число кластеров, да, заранее задается, сколько, на каком этапе мы хотим остановиться, сколько кластеров получить. Ну вот здесь, например, 2 кластера, дошли до 2 кластеров. Получается вот такая иерархическая кластеризация. Значит, другой класс кластеризации, он связан с оптимизацией конфликта, вот о чем я как раз говорил. В этом случае по-разному поступают. Ну, например, можно выделить некоторое маленькое подмножество фокальных элементов, вот альфа-штрих, ну, которое из таких значимых как бы фокальных элементов. Что такое значимый, сейчас я поговорю об этом. Но и потом после этого можно перераспределить остальные, например, фокальные элементы, отнести вот к этим значимым, мы получим тогда такие какие-то кластеры. Либо можно использовать вот какой-то аналог алгоритма Каминс, например. Ну вот что касается первого подхода, да, когда мы выделяем значимые элементы, то вот в прошлом году как раз с моим соавтором Андреем Броневичем вышла вот такая статья, где в том числе, ну там она не только этому посвящена, но в том числе был предложен такой алгоритм, основанный на так называемой функции плотности конфликта. Значит, плотность конфликта – это такая функция, которая принимает большие значения в данном множестве, если рядом с ним, грубо говоря, нет пересекающихся множеств, да, либо нет сильно пересекающихся множеств. Ну, вот в идеале функция равна единице принимает максимальное значение, если таких вообще нет. И наоборот, нулевое значение, если это множество пересекается со всеми другими множествами из множества фокальных элементов. Ну, третье условие – это условие линейности для простоты. Так вот, если такую функцию конфликта, да, можно нетрудно показать, что такая плотность, она будет как раз равна вот единице минус функция правдоподобия, вот та, что там, о котором я говорил, которая является верхней оценкой вероятности события, она тут будет так вычисляться. Ну и кроме того, можно еще учесть массу самого фокального элемента, то есть нас интересует не только фокальные элементы, которые конфликтны с другими, но еще и большую массу. Ну и тогда алгоритм будет такой довольно простой. Мы упорядочиваем все множество фокальных элементов по убыванию вот этой функции плотности конфликта. И, значит, выбираем значимые конфликтные элементы, начиная вот в соответствии с этим порядком. Ну и кроме того, используем еще функцию расстояния, так чтобы рядом 2 фокальных элемента из этой последовательности, находящихся рядом, чтобы они не попали вот в это множество А', не попали. То есть используем какую-то метрику. Что касается метрики, ну, можно использовать, конечно, метрику между фокальными элементами, как вот мощность симметрического разности множеств, либо если это измеримое пространство, то это какая-то мера измеримой разности множеств. Если это метрическое пространство, можно использовать вот метрику Хаусдорфа. Но вот чаще используют вот такую метрику, очень популярна вот в этой теории, вот такая метрика, которая с вот индексами Джакарда. Тут такая билинейная форма. Это действительно метрика. Можно доказать, что это настоящая метрика. Вот она чаще всего используется. Да, этот алгоритм, конечно, имеет вот свои аналоги, такие точечные. Да? Ну вот, например, один из таких алгоритмов я тут привел ссылку, но таких алгоритмов довольно точечных много. Да, ну вот если тот же пример использовать, то в результате мы получим два вот таких кластера. После этого можно, как говорят, решая задачу минимизации расхождения между исходным телом свидетельств и вот нашим телом свидетельств с какими-то коэффициентами неизвестными, найти эти коэффициенты, мы в результате получим очень близкий результат к тому, что было у нас в иерархической кластеризации. Очень близкий, там было 0,7, 0,3, ну а здесь чуть массы чуть-чуть другие. Так, да, ну и можно вот в общем случае решать задачу перераспределения фокальных элементов среди по кластерам, по выбранным кластерам. Ну, решать ее следующим образом. Значит, вот с каждым выбранным кластером можно связать свое тело свидетельств, ну, которое строится вот таким образом. Масса того элемента, который у нас был в исходном теле свидетельств, совпадает с исходной массой, ну, тут тогда сумма всех вот этих масс по всем внутри кластера, она не будет равна единице в общем случае. Поэтому оставшуюся часть массы мы отнесем на массу всего множества. Это наше вот то, что мы говорим, незнание. Масса всего множества. То есть вот так можно, как говорят, натянуть на вот этот кластер, натянуть тело свидетельства. Тогда вот алгоритм перераспределения оставшихся фокальных элементов по выбранным кластерам, вот по выбранным кластерам А', он будет следующий. Мы берем, значит, очередной фокальный элемент, присоединяем его к какому-то кластеру, потом натягиваем на вот этот новый кластер соответствующее тело свидетельств и считаем конфликт между новым вот этим телом свидетельств и всеми другими телами свидетельств. И для тех, значит, это будет такой как бы внешний конфликт между кластерами мы получим. Да? И в том случае, когда мы получаем максимальный внешний конфликт между кластерами, вот тому кластеру будем относить этот фокальный элемент. То есть тут есть вот полная аналогия с принципом компактности. Да? Принцип компактности вот классически говорит, что мы должны в один кластер поместить те элементы, которые близки друг к другу, в разные кластеры, которые далеки друг к другу. Вот здесь вместо метрической характеристики близости используется конфликтность. То есть в один кластер относим те фокальные элементы, которые мало конфликтны друг с другом, а в разные, которые сильно конфликтны друг с другом. Так, ну и да, вот в результате такой кластеризации мы получим вот такую кластеризацию, которая вот цветом обозначена здесь как раз. Это будет примерно соответствовать тому, что было в иерархической кластеризации, внешняя кластеризация. Так, ну и, наконец, Каминс. Вот совсем коротко, я так понимаю, времени у меня почти не осталось. Значит, в этом случае вот рассматривается функционал минимизации суммарного внутреннего конфликта между каким-то центром кластера. Сейчас я скажу о нем, что это такое. Центр кластера – это тоже тело свидетельств. Вот тут, что интересно, это не фокальный элемент какой-то, а это именно тело свидетельств, то есть натянутое на какие-то фокальные элементы. значит, телом свидетельств, натянутым на элемент этого кластера, вот такой функционал минимизируется. Значит, что касается, тут самое интересное, ситуация с центрами кластеров. Значит, центр кластера, если искать его вот в таком виде, как линейная комбинация категоричных тел свидетельств из этого кластера, что естественно, то тут вот нетрудно доказать такую теорему, что вот этот функционал при фиксированном разбиении, но мы меняем центры кластеров. Да? При фиксированном разбиении будет достигать минимума, когда центры кластеров строятся следующим образом. Строятся вот по этой формуле, естественно, один. Но вот в качестве множеств А тут выбираются такие множества, которые максимизируют вот такую функцию правдоподобия, суженную на этот кластер. Сужение на кластер эту функцию правдоподобия максимизирует. Да, ну и в этом случае мы получаем вот как бы классический, используем дальше классический алгоритм Каминс вот с такой оговоркой. Единственное, что тут сложность заключается в том, что вот эта теорема, что вот в отличие от метрической ситуации, вот здесь, как правило, возможно множество решений, множество коэффициентов будут удовлетворять условиям этой теоремы. И множество центров кластеров мы получаем. Не один центр кластера в этом случае. Чтобы, ну, можно, в принципе, работать и с таким множеством, ничего страшного. Но если мы хотим все-таки сузить, добиться, чтобы там у нас был один центр кластера, то нужно использовать какие-то дополнительные процедуры, дополнительные условия. Это могут быть разные условия, например, условия минимизации покрытия. Да. В общем случае мы получаем не разбиение, а покрытие фокальных элементов. Можно использовать условия минимизации покрытия, то есть чтобы покрытие было близко к разбиению. Ну, например, вот такое условие нужно минимизировать суммарную мощность кластеров. Либо минимизировать какую-то меру неточности, вот, например, такую. Либо минимизировать, ну, в общем, разные есть варианты дополнительных процедур, которые позволяют выделить из вот этого множества центров кластера, выделить в каждом кластере по одному центру. Так, ну вот, например, на том же примере, если посмотреть, то получается, ну, тот же самый, в общем-то, получается результат. Так, ну вот, собственно говоря, и все, что я хотел рассказать. Да, вот как дополнительный бонус можно использовать вот эту процедуру кластеризации для оценивания меры внутреннего конфликта кластеров, меры внутреннего конфликта тела свидетельств. Вот когда мы кластеризацию получим, то посчитав внешний конфликт вот для тел свидетельств, натянутых на эти кластеры, мы получим меру внутреннего конфликта, которая вот в общем случае она считается как бы сложнее, чем мера внешнего конфликта между кластерами, неоднозначно. Поэтому вот это такой довольно важный момент. Так, ну вот, пожалуй, и все, что я хотел сказать. Reference и happy birthday, Борис Григорьевич. Все. Если есть вопросы, я готов ответить.
Подходите к микрофону, заодно проверим микрофон.
Раз, два.
Да, конечно.
Ну да, ну, мы с вами на двоих тогда будем говорить. Значит, я не очень понимаю, где взять эти данные. Вот исходные данные для этого кластеринга. Как они получаются?
Это могут быть, например, экспертные оценки. Вот первое, что это экспертные оценки. То есть мы там, например, выбираем там кого-то, да, какого-то руководителя выбираем, да, и там опросили коллектив, да, столько-то человек сказали, что они могут, например, не ответить так, что мы не можем выбрать кого-то одного. Ну вот мы из 5 кандидатов я склоняюсь больше там к первому, второму, например. Другой скажет, что я из 5 кандидатов этих склоняюсь там ко второму, третьему. да, и так далее. Мы получаем вот эти множества. Ну, это такая простая ситуация. Либо это, например, если речь идет там о прогнозировании каких-то, ну, например, прогнозирование там стоимость акций, там какая будет, например, там через месяц, да, то есть эксперт говорит о том, что стоимость акций будет, ну, в каком-то интервале лежать, например, там от 40 до 50 единиц. То есть вот это уже будет фокальный элемент. Он не говорит, что это стоимость акций будет там 45 единиц ровно, да, точечное значение не дает, а он говорит множественное значение в виде интервала. Вот это уже будет какой-то фокальный элемент. Какой-то, либо он говорит, например, от 40 до 50 степень уверенности большая, где-то примерно 0,7. Ну, может быть, там, допустим, от 48 до 55 со степенью уверенности 0,3. Вот, например, вот такого типа.
Спасибо, я понял. Спасибо.
Сообщение посвящено управляемости треугольными системами со сменами фазового пространства. В двухфазовых пространствах x и y разной размерности. Пространства могут иметь как одну размерность, так и разную. Возможен переход как из пространства большей размерности в пространство меньшей размерности, так и наоборот. В фазовых пространствах x и y движение описывается следующими системами. В пространстве x движение описывается системой 1 на отрезке времени 0 тау. В пространстве y движение описывается системой 2 на отрезке времени тау t большое. Интервалы времени тау и t большое заданы. Системы 1 и 2 были рассмотрены Коробовым впервые и названы треугольными. В дальнейшем они тоже им рассматривались и также изучались, например, в задачах стабилизации каскадов систем. К подобного вида системам сводится ряд физических управляемых процессов. И допустимыми управлениями являются непрерывные функции u и v со значениями в R1. Также нам задано в пространстве x, нам задано начальное множество, гиперплоскость перехода, не пересекающей с начальным множеством m0. Задано отображение q, с помощью которого осуществляется переход из одного пространства в другое. И в пространстве y задано конечное множество m1, не пересекающееся с множеством q от гамма. Движение объекта осуществляется по следующей схеме. Пусть на отрезке времени 0 тау объект движется из начального множества m0 пространства x по решениям системы x1. В момент времени тау объект попадает на гамма, и под действием отображения q происходит переход в пространство y. Мы получаем точку y от тау, которая является начальной для движения объекта в пространстве y. Дальнейшее движение осуществляется на отрезке времени тау t большое по решениям системы. Это я делаю? По решениям системы 2 на множество m1. Причем y от тау не принадлежит m1, иначе задача решена. Задача заключается в том, чтобы найти условия, при которых объект, описываемый системами 1 и 2, будет управляемым на отрезке 0t большое из начального множества m0 пространства x в конечное множество m1 пространства y. А объект, описываемый системами 1 и 2, называется управляемым из m0 в m1, если существуют такие допустимые управления u и v, что соответствующим решения систем удовлетворяют граничным условиям. Следующая теорема дает достаточные условия управляемости данной системы, и в ходе доказательства удается получить непосредственно траекторию, которая связывает начальную точку в m0 и точку в m1. Если мы в пространстве X рассматриваем систему, вводим замену переменных следующим образом. И через zn плюс 1 обозначаем новое управление. После такой замены система 1 приводится к линейной системе, которая в силу рангового критерия Калмана является полностью управляемой за время тау. А по определению полной управляемости у нас существует управление, которое переводит объект из начального множества m0 в произвольную точку гамма. Тогда мы новое управление можем выбрать в виде функции от времени t, таким образом, чтобы за время тау попасть из точки z0 в точку z от тау. Например, его можно выбрать вот в таком виде. Далее, подставив в левую часть соотношения 1 и 5 и вместо переменных полученные функции и управления, мы последовательно находим функции x1 и xn и получаем траекторию, которая удовлетворяет ограниченным условиям. Далее мы переходим в пространство y под действием отображения q и в y рассматриваем аналогичное движение. Проводим аналогичные процедуры и получаем второй кусок траектории, который соединяет точки уже в пространстве y. И таким образом мы получаем управляемость объекта из m0 в m1 и траекторию, которая соединяет начальное и конечное множество. Я ряд ссылок на литературу и спасибо за внимание.
Thank you. Boris Grigorovich, I would like to congratulate you and wish you good health and wealth. It's a bit pity that I'm speaking to to nobody instead of you, but I hope you hear me. And Boris Mirkin was my teacher, my lecturer, and as students we always liked his lectures, enjoyed them. They were very interesting. We appreciated his sense of humor, and Boris Grigorovich always had many students with projects, and I remember that very well. So it's a pleasure for me to stand here and present my research project. So it is a bit different from what we heard previously. It is devoted to the problem of group decision making. The problem which Boris Grigorovich has also contributed to in the beginning of his academic career. The problem is the following. We have a group of individuals, and they need to make a collective decision to choose a candidate among a group of possible candidates. And there is a problem with in this framework that voters may misrepresent their preferences in order to achieve a more preferable result. That's called manipulation problem in social choice. So in some sense it is natural and logical, because if voters can influence an election result, then they have possibility they have an opportunity to influence the voting result, and the possibility of manipulation is a consequence of this. So there is a famous theorem, Gilbert-Satterthwaite theorem, which says that every natural, every fair voting rule, which considers at least 3 alternatives as a possible result, they are manipulable, and non-dictatorial voting rules, they are manipulable. But if all non-dictatorial social choice rules are manipulable, then it is of interest to know to which extent they are manipulable, they are susceptible to manipulation. And a very widely used approach to solving this this problem is calculating the probability of manipulation. So to calculate the proportion of preference profiles, so possible situations where manipulation is possible. So for example, for m alternatives and n voters, there are m factorial power n possible possible preference profiles, possible situations with possible distributions of preferences among voters, and we calculate the proportion of manipulable ones. We consider also the problem of manipulation under incomplete information. So we add this assumption to make the model more realistic to some sense. So voters don't know the all preferences of others exactly. They just know some information about a preference profile. And if a voter has an incentive to manipulate in profile P, preference profile P, but it doesn't mean that his manipulation is successful in this profile, because he or she doesn't know the result exactly. He just has some information, and he or she, a voter, has an incentive to manipulate if in the set of all possible situations he has an opportunity to improve his result, at least in some of them. So that's, in simple words, we will see this in detail further. So I'll explain shortly the framework. Let the n be the number of the set of voters, and the number of voters is denoted by small n. X is a set of alternatives. So the cardinality of this set is m. Pi, this is the notation for preferences of voter I, which is a linear order. And P, bold P, is a preference profile. We consider aggregation rules in the following. Social choice correspondence is a rule which takes a preference profile and as a result gives a subset of alternatives, some subset of winning alternatives, which are the best according to this procedure. Since there could be subsets, we apply a tie-breaking rule to choose the unique winner. This rule is assumed to be alphabetic, so there is some predefined order and we choose from a set A one alternative which is not dominated according to this order, which is denoted by PT, tie-breaking order. Social choice rule is denoted by F, is just a tie-breaking rule applied to a social choice correspondence, just to pick one alternative, one candidate. And we consider 4 types of public information. The first one, profile, it's complete information, when we know everything about a preference profile. So the poll information function pi of P is a function for public information, what we know about preference profile P. A rank PIF, poll information function. It's a function that returns a ranking of alternatives according to this very rule. The rule is also known. Winner PIF returns. I'm sorry, there should be C of P here. Returns a subset of alternatives which are winning. And a unique winner PIF returns a unique winner after a tie breaking. So there are 4 types of poll information functions. And what does it mean for a voter to have an incentive to manipulate? He has an information set. So that's a set of all possible situations or preference profiles of all other voters that are consistent with his information, with information he has from public sources. So that's his world in some sense. The definition of manipulation, if it's a coalitional manipulation, or no, it's an individual manipulation, when an individual has an incentive to manipulate. If in his information set there is such a preference profile that such that changing his preferences to P tilde, he may get something better and he will not get something worse as a result. So there is a possibility to improve the result of voting procedure, and there is no chance to get something worse. The probability of manipulation, of individual manipulation, is denoted by index I with small index ind. The probability that in a preference profile randomly chosen from the set of all preference profiles there is at least one voter that has an incentive to manipulate under this voting rule. And what does it mean to have an incentive to manipulate within a coalition when we consider coalitional manipulation? A voter, each voter has a set of of other voters who have the same preferences, so his coalition, co-minded people. And if all his members in this coalition change their preferences in the same way, and they can achieve a better voting result, then they all have an incentive to manipulate. And as in the previous definition, they don't have a chance to get something worse from their manipulation. So that's a way a voter can think about other voters' actions in in the framework of incomplete information. So we consider several social choice correspondences, social choice rules. Among them are there is the most important class of scoring rules, which are defined by a scoring vector. And Sj in this vector denotes the score assigned to any alternative for its jth position in individual's preferences. So S1 denotes how many scores it gets for the position, for the top position, for the first position in preferences. Sm denotes how many scores it gets from the bottom position. And we sum these scores over all voters to get the total score of each alternative. So the most popular rule is plurality, for example. We assign exactly one score to each alternative for the top position, and we assign 0, we give 0 scores for any other positions. So we count just the number of top positions for each alternatives. In veto rule, we minimize the number of bottom positions for alternatives, and in this case we need to give one score for each position which is not bottom position to any alternative. So we just give 0 for the bottom and 1s for every other position. And border rule is the following. We give m-1 alternative for the a score for the first position, and then we give m-2, m-3, etc. until 0 for the bottom position. So why I explain in such details these rules? Because the main results of this research are about scoring rules. For example, this one is the asymptotic behavior of manipulability index for individual manipulation. So the probability of individual manipulation under the information, public information about the unique winner for plurality rule, the most popular one. When we use alphabetic tie breaking, then when the number of voters approaches infinity, goes to infinity, then this index, this probability, tends to 1. So it means that in almost in every possible situation, you will have an individual, at least one individual, who has an incentive to misrepresent his preferences. So it couldn't be called protected from manipulation, this rule, for example, under this very kind of information. For when you change the type of information to winner, so it means that we know a set of winners, then this value depends on the number of alternatives. This value which this index approaches to when the number of voters goes to infinity. It is 1 minus 1 divided by m. So we change the type of information, and we immediately change the number of possible situations which are susceptible to manipulation. This is coalitional manipulation. When we switch from individuals to coalitions, then this index again is equal to 1 in asymptotic. With alphabetic tie breaking, almost in every situation again we'll have at least one voter who has an incentive to manipulate to vote strategically and sincerely when he thinks about his coalition members. So when he feels some support from co-minded people. That's the asymptotic behavior of border rule. It's again one for coalitions. And we proved that for any number of voters and any number of alternatives, the probability of coalitional manipulation equals the probability of individual manipulation when we have information about a unique winner of the election for all scoring rules, for every scoring rule. So, and we conducted some computational experiments just to view, to observe how these indices behave, and you may clearly observe it that, and compare the left-hand side graph illustrates individual manipulations, the probability of individual manipulation for plurality rule, and different kinds of public information. And on the right-hand side, you can see coalitional manipulability index. And you see that for individual manipulation, we see only one graph approaching 1. It's the graph. It's a line corresponding to the information which is the least perfect. So it's information about the unique winner. And this graph illustrates the first theorem. The first theorem in our slides. And for coalitional manipulation, we see this tendency. I think maybe even for all of these graphs, this one approaching tendency. And what else we could see? That the less information we have, the more the greater is the probability of manipulation. So so in more situations, at least one voter will have an incentive to manipulate it. It is it's the course is that information is not perfect, but it's useful. That we have from that we have this here. Sorry. So just the same situation for border rule. I will not consider it. And Vita rule. Vita rule is we considered it, defined it, and it's in some sense it is an exceptional rule, because for when we restrict information, when we give less information to voters, and when we switch to coalitional manipulation, this index for this very rule is getting smaller, is getting less. And for most kinds of information, it is almost 0 or equals to 0 in most cases. So Vita rule is, in some sense, it is protected from manipulations of individuals and coalitions, and from manipulations under incomplete information, in such a way that in most situations the manipulation is impossible in this rule. So that's these are the main points of my research. Thank you very much for your attention. I would be happy to answer your questions.
You
have said that
it will be good if you come more close here because the voice.
No. I may.
It's okay.
Can you hear me now?
Yeah.
So you told that the preference profile was selected randomly, right? So and you have done some computational experiment as well. So may I know what was the sample size of this preference profile?
Oh, in fact, the sample space was the set of all preference profiles here, and I just created the set of all of them. So that's why I conducted an experiment just for the number of voters up to 15. And that was my limit for this.
And another question that when we are adding the all scores to getting the final voting score, as you mentioned, but previously you told that the one voter may be aware to the other voter actions and he can think about it. So don't you think that in this case then the voter might be influenced by the scores are independent? What do you think?
What is independent? What?
No, my question is that why the voter is getting the chance to think about other voter actions?
He just thinks that voters with the same preferences as he has, they are identical to himself, and in this, in some sense, their incentives then are identical too. So they all these voters of the same type have the same incentives, and they want the same candidate to win. So that's why they may misrepresent their preferences in the same way. And this is what our manipulating voter takes into account. He's saying things that, what if all my coalition members will also change preferences in this way, and then will collectively achieve something better in this sense.
Okay, thank you.
I wanted to suggest
Thank you.
another avenue for
A little bit harder.
Yeah, I wanted to suggest another avenue for research. You could perhaps consider what portion of the population need to have the same preference for them to be able to manipulate the whole vote to a certain result. For example, the second best candidate wins, or the third, something like this.
Yes, yes.
Perhaps this would be interesting.
Yes, yes, of course. Thank you.
Any
also
other
think-
questions? Please. Could you come here? I invite you personally. Because the microphone is too far, and you are the next speaker, by the way.
So for online participants to hear the question.
Yes, please.
Yeah, I want to ask about the population size. Like looking at these scales, your population size is limited to 15
Right,
samples.
right.
And when we look at the curves, they are quickly converging.
Yes.
How representative is this finding? Let's say we increase the value to 100 or 1,000 samples.
So these experiments are conducted for the case with 3 alternatives, you see, and the number of voters from 3 to 15 everywhere. And for this case, we observe some tendencies. So it's just for illustration results. which we obtained for general M and N. So you see these results are for any number of alternatives. When we have infinitely we have a number of voters tending to infinity, then this holds. But I couldn't say something for sure for other kinds of public information. You see, I haven't proved for example, for rank function or score function, so I couldn't say anything. But graphs show that it may also tend to one or to something. So have I answered your question?
Yeah, certainly, to some extent. No, thank you.
Thank you.
Any more questions? Okay, thank you very much.
Thank you.
Our next speaker is Tendai Chikake. He said,
Yes. Good afternoon, colleagues. I shall apologize for my voice. I think I caught a cold. My name is Tendai, and I collaborate with Professor Boris Goldengorin, and I want to present Pseudo-Boolean polynomials for dimensionality reduction and image processing on celebration of Professor Mirkin's birthday. So I shall start. Now, the purpose of this talk is to showcase the usage of Pseudo-Boolean polynomials formulation for those shortlisted tasks. It is a new formulation or a new technique or approach to actually solving these tasks. So the main one is invariant dimensionality reduction, which we then use for purposes of cluster analysis, outlier detection, and feature selection. Then the other task is dedicated to detecting edges and blobs in image data, which we can use as well for image segmentation, as well as optical character recognition. So I think I'm not going to explain how you formulate the Pseudo-Boolean polynomials, because I think you already realized yesterday from Professor Boris Goldengorin. I will just go to the properties that we desire to use for these purposes. So when we reduce a sample or an input matrix in Pseudo-Boolean formulation, the basically three properties that arises, which I think you realized yesterday. There was P equivalence, there was P truncation, as well as compacting the initial data. So now the compacting property is the one property that we want to use for invariant or lossless data compression. And then P equivalence, we desire to use that for similarity comparison, in the sense that a Pseudo-Boolean polynomial would be a low dimensional embedding of the initial data. And also there is gradient shift detection. Like in an image, we understand that when there is a change of color in the image matrix, we want to detect that. And by formulating the Pseudo-Boolean polynomials, we select some patches of a given size, and then we check the power or the order or the degree of the resulting Pseudo-Boolean polynomial. If it is higher, it shows that the patch is overlapping an edge. If it is lower or equal to 0, that means there is basically same information, same color. I will show in the following slides. Why do we desire to use Pseudo-Boolean formulation for dimensionality reduction, which we then proceed to use for clustering or unsupervised classification? we noticed that the other alternative tools that are available, for example, the T-distributed stochastic neighborhood embedding, TSNE. Yes, they work fine for a number of selected cases. However, they have this non-convexity. There is a cost function involved. So the results might differ by differing the input values that we initialize during the formulation of the dimensionality reduction task. This results in variance. There's also the other limitation of dependence on the whole population of samples. For example, using principal component analysis, we have to calculate some densities across each and every sample, and then make a distance function to compare, and then determine that, okay, this is the lower dimensionality of this value, and penalize those which have the smallest distance. However, with pseudo-Boolean polynomials, then we operate every sample independently, one at a time. It does not involve any other information of any other sample in the population, and there is no variance because the only input data in the formulation is the data that is describing that sample. There is nothing, no epsilon or whatsoever. So now, when we reduce, let's say, a data structure which is, let's say, 4 dimensions, 5 dimensions, our desire is to reduce it to, let's say, 3 or 2, because we can easily plot these dimensions on paper or on our computer screens. And then once we have this low dimension, we can actually like find some lines that separate samples just by plotting, and then find the best separating line or the best separating plane in a Cartesian space. I think usually, let's say, for example, this very popular dataset, iris flower dataset, is often used during the introduction to machine learning or data science, etc. And we all know that it is four-dimensional data. Why do we say four-dimensional data? Because every sample is described by the sample length in its width, as well as the petal length and the spatial width. Now, if we are to understand if there is any linear relationship between these particular values to the label that this flower depends to vesicolor or setosa or Vichiniku, we realize that it is difficult. But now we decided that why don't we create an embedding that allows us to find an incidence of these particular dimensions, whereas the physical physical feature, like the sepal and the petal, they're represented as rows with incidence with their physical quantities of length and width. And then by looking at this, we realize that we already have a typical input to a formulation of pseudo-Boolean polynomials. And I would like to outline in this scenario that, of course, our method is not universal, because we desire that our information is in matrix form. And there is also, and the matrix form makes sense, like the sense that the incidence values, they are related. Right, in this figure, I would like to highlight to you that each sample is reduced. Let me go back to the previous slide. Each sample is reduced, if you can see. I need a marker here. Oops, it's not writing. Marker. Right, this sample ID 1. When we process it through a pseudo-Boolean polynomial, it reduces to this value 6.0, 2.4y2. And all the other values, they also reduce into a characteristic like this. And then this aggregation, when we take it and express it as Cartesian coordinates, we can actually find some lines which separate these samples, and we denote that there is a single outlier, which we looked at it and realized that it is a particular outlier. And then there is also the other values, I think here, they are very close to each other. We had to find some line that's best separate this. But looking at this, we realized that just by finding these separator lines, we can actually achieve a clustering after reducing this data into lower dimensions. And then we would also like to show in a more practical scenario the Wisconsin breast cancer diagnosis dataset. In this dataset, we have 30 features that describe a certain sample. And that is a very huge dimensionality. So we find how best we can represent this as a matrix that can input to the pseudo-Boolean polynomial. In this scenario, I also would like to show that this is an example where we show the feature selection or feature dropping technique that results from this formulation. Now, this typical sample, for example, that you see here, it is reduced to this polynomial, and this is the characteristic polynomial for each and every sample in the dataset of 159 samples. And this automatically represents an XYZ vector, which we plot in the Cartesian space. And looking at this, I think this aggregation, we managed to drop, I think, 2 or 3 features so that we would find a line that best separate these samples. And it's an accuracy of close to 95.4% linear clustering. If we had taken this, we also experimented by taking these reduced samples through an approximation technique like support vector machine or k-means. We actually can get even higher scores, but our another goal of our research is to remove these approximations so that we can have invariant processing of our data. Now we go to the image processing part. Here we are particularly interested in a gradient shift that results by formulating pseudo-Boolean polynomials. The property that we want to exploit here is the degree property of the resulting polynomial, and it allows us to detect whether a certain page that we have processed in the data is over an edge or it is over a blob region in the image data. It is also helpful to us, like we want to also extend P equivalence so that we can go into object detection actually. It is ongoing research. Now, the algorithm is that we take the image matrix and then we extract some windows, sliding windows, or rather page of some literal size. Let's say 3 by 3 as shown here, or we take 8 by 8. It's just conditional. It's conditional to how much sensitive we want our edge detection to be. Now, let's say this region, the first region that I colored here, it has only 5 values. These are constant values. And since the pseudo-Boolean formulation that we use here is penalty based, all the other values will aggregate to 0 because we're subtracting down the row. And then summing the first row, we get 15. And this means we have a 0 degree. There is no variable here. But looking at the other matrix here, it is different values that we processed, and it results in a polynomial with the degree of 2. Here, this is the maximum degree. So we because it is happening due to the fact that the other rows are overlapping like the data that is differing in color on the image matrix. So we already indicate them as overlaying an edge. Now, practical examples that we did. For example, here I show a comparison of this edge detection processing comparing with the Kani method here. You would see that the Kani method allows us to just find the outward edges of this paper fruit in the input image here. But using pseudo-Boolean polynomials here, we can actually see the depth because if you look at this 3D representation of these degrees, it shows that okay, this region is 5. It's power 2 or power 3 or power 0, and you can have a projection actually in 3D while at the same time achieving the edges that you would desire. We also experimented in image segmentation task with the Dubai satellite data set. And I would like to highlight the pre-processing that we were doing here, a Gaussian filter and a threshold of a pixeling threshold, so that our input values, they are limited at least to a range of 0 to 10 or instead of 0 to 255. And this is the result that we have. Of course, we still need to go to the part where we have to detect that this region, it is a water body, and this is a road. We're still working on that, but the edge part of detecting it in segmentation, they are impressive results, I would say. So in summary, I would like to say that our proposed methods, they are explainable and combinatorial. I think in the medical sense, for example, in the Wisconsin data set for breast cancer, somebody would desire that they have a diagnosis which was approximated by this method because it is explainable instead of, let's say, a k-means or a vector machine algorithm. And then also we have the invariance to initialization of parameters and independence of sample population in dimensionality reduction. And also very much controllable or flexible inputs to image segmentation or edge detection. In the future, we propose to exploit the p-equivalence property for actual object detection. We hope to use probably the resulting pseudo-Boolean polynomials is lower dimensionality embeddings for the neural network, for example, and also exploit this agent blob detection to optical character recognition and interpolation of 3D data from 2D image data. If you desire to understand much about the formulation of pseudo-Boolean polynomials, I recommend this book, Data Aggregation for P-Medium Problems by Albert Wine and Professor Boris Goldengorin. There's also cell formation in industrial engineering. It is a very good book to understand the whole process of pseudo-Boolean polynomial formulation. For this, I thank you for your attention. I can listen to your questions.
Thank you very much. I would like to thank Tendai for his contribution to the abstract book of the conference. So many changes. He was patient and he really independently. I really appreciate his contribution and give to this very, very frequently changed schedule. I apologize and thank you, Tendai, again. Maybe you have some questions. We have plenty of time. You're welcome.
Ladies first.
All right. Could you please clarify how is the degree of the polynomial connected to edge detection? I understand that the higher the degree of the polynomial, the more likely that there is an edge, but why?
Yes. The thing is, can you help me? I need to open this presentation of Professor Goldengorin. Like if you noticed from yesterday, the formulation of the pseudo-Boolean polynomial, is we are subtracting the data like going. We are trying to minimize the cost of initial matrix, right? And we are penalizing the least expensive feature or the previous one. In such, can you open the presentation from Professor Goldengorin? So that penalizing feature, when we apply it into image processing, we are now saying that the previous image or the previous row in this page was less expensive or less expressive. Let's say, for example, if it is a color 10, it is close to black, but it is a 250, then it is close to white, right? And the 250 is more expressive, and it shows that there was a gradient shift from this value to that value. And whenever there is values which are transitioning from a smaller to a higher value, or from a higher value to a smaller value, there's yes, there is definitely gonna be a variable, a monomial, like a variable attached to that monomial. Here, I think, yeah. If you look in this processing, here we have created our delta C matrix, and then we are utilizing the permutation matrix, and we are utilizing it to represent our variables. When there is a difference between the previous value and the previous value, we definitely gonna have like another y1 or y2 or y3. So that is indicative to a change in there is a shift of values. That's why we decided that it represents an edge. Yes.
You're welcome. Your questions, please.
Perhaps I missed something, but I didn't see any formal definition of what is Boolean polynomial.
Let's go to the next, I believe, 2-3 slides, and there is an example. No, this is a combinatorial formulation. Just after the numerical example. First, I believe, 4 slides, something. You can stop here. Вот пример, как выглядит псевдо-булинский полином для 5 столбцов и как он построен.
What is y1, y2, it's Boolean or the continuous variable?
Нет, это все дискретные переменные. Y это 0,1, 0, когда строка доступна, или, скажем, кластер открывается в этой строке, и 1, когда недоступна, и не открывается кластер.
Потому что коэффициенты не нули.
Что?
Коэффициент can be arbitrary.
Нет, коэффициенты нет. Коэффициенты как раз показывают, как изменяется монотонность внутри каждого столбца. Они равны разности между следующим элементом и предыдущим. А константы отражают минимальный элемент. В случае, если нам важна, ну скажем так, не монотонное неубывание, а наоборот монотонное невозрастание, тогда у нас просто или задача максимизации чего-то, то у нас просто будут другие значения коэффициентов, больше ничего. Ну и, соответственно, перестановка будет в каком-то смысле обратно. На максимальном месте будет стоять минимальный и наоборот.
Sorry, probably it's a bit stupid, but can you
Maybe
clarify?
you can come a little bit close to the mic. I apologize.
No, it's good.
Because the connection is not really good.
Okay. Well, can you go through one of the... How do you derive the coefficients y1, y2, y4?
Tendai, please. This is very good question.
Yeah.
Go ahead.
And then I will ask the rest of questions. Okay.
Okay, here is the process of Pseudo-Boolean formulation. This is our initial cost matrix, and we want to find in our task, let's say for example for image segmentation, we want to minimize the expressiveness of this matrix, and when we go with the values down this column, we realize that there is let's say 11 value, for example, which is less than 16, which is like in the third column, and then we sort each column. Yes, yes, in a non-decreasing order, and then we generate this. Sorry, we generate the permutation matrix here, P1. Then that indicates like the indices of the.
Okay. See, which constructs the complete matrix. But it is just enough to understand for one column.
One column would be enough?
Yes. No, enough to understand. Because
Okay.
all others just
Yeah.
they're repeating the same.
It's I'm very sorry, but I don't understand how this permutation P1.
Look at the middle part.
1, 2, 4.
Can you see in the middle part the
Yes.
permutation?
Yeah.
Can you see that the permutation shows the ordering in non-decreasing order of the entries in the first column?
Oh, okay, I see
Can you
what
see
you
that?
mean by permutation. Okay, I got it. Yeah.
And another one at the
This is the
completely
index of the rows. Okay.
right
Exactly.
Okay, now I
up
understood.
delta C. This is another. Here you
Yeah.
can see the coefficients.
Mhm.
So at the first place, always for any say column, we have the smallest element,
Yeah,
and then the difference between
Okay,
the
now I
next and
understood
previous,
this.
next and previous, and the Boolean variables shows us whether we are activating, say, the row corresponding to the smallest or to the place where the minimum is located. For example, 7 is, okay, it is not interesting. 4 in the third column is located at the second place. That what it means? It means that in the permutation, in the matrix, it is not on this slide. Maybe you can go ahead and I'm not sure whether oh no, it is shown only for the first column.
Okay.
Just oh no, very good. Thank you, Tendai. So it is. Can you see? It is just straightforward indicated in the deltas and in the corresponding permutation
now I
where it is
understood.
located at the second
now I
place.
understood. Okay.
That's all. It is the smallest, yes, because in the permutation itself, it is located at the first place. That's all.
Okay. And now in edge detection, you say, well, if I'm wrong, please correct me. You say that the maximum degree is 2. We cannot have higher degree because the window is.
Yeah, no. Now the window determine, for example, what can be the maximum.
Oh, sorry. Well, the maximum is is the window size.
Yes.
Minus 1.
Yeah, because for example here we have 4 columns, so the maximum possible is 3. Yes.
Did you compare your the performance of your algorithm, for example, with well-known? I missed it with well-known edge detector algorithms like Kenny or I cannot remember many of them, but there are at least 3 or 4 of them.
Yes. Yes. I would say the formulation itself, Pseudo-Boolean polynomial formulation, it is a polynomial. And then if you have, let's say, very small instances, let's say 8 by 8, that is very, very fast. And on an image matrix, of course.
I'm asking about the quality. How did you compare the quality of your detected edge with Kenny?
The quality, how would I say? We did a qualitative analysis of
So you did it
visually, yes.
Okay.
Okay, I have one question here.
Yes.
you have used, you have exemplified the WBDC is data set, right?
Yes.
WBCD data set. And you have got the accuracy 95.4%.
Yes.
Okay, so now, and you have also recommended a few things for object detections and edge detections in your last slides. But for this classification problem, means as he was talking about the comparison, that's why I'm telling the normal in other models, if you compare with the other models, we are getting 99.5, 99.7, even if we use neural network, we are getting that type of accuracy. And with the optimization of VST. Now, my question is that, is there any room to improve the score in case of this types of, because you have already recommended something for object detection and the edge detection, but what about this type of problems?
Yes. If you locally say, for example, DB-scan, there is a neural network. I saw it in a certain paper that they used to cluster the iris dataset, and they claim that they have 100% accuracy, but that is wrong, because there is a specific outlier. I think I showed in the output figure of the classification. There is that outlier, and it is it is there. So it doesn't make sense to say that is 100%. That is overfitting, right?
No, that is fine. I'm not talking about 100%. But the thing is that, did you split your data set as a trained data or test data? When you have taken this 95.4% accuracy, means on which data set have you measured it? Have you split out your data set in test and trained set?
Yes. Now, like for example, the way that I say that this processing is invariant. The same output of pseudo-Boolean polynomials will be output for the same given input matrix. So even if I change,
I also have a question on that.
yes, if I change the data set training and inference data set, I will still have the same output value.
How can you measure the overfitting? Whether this model is overfitting or underfitting, you cannot measure. You have to put some space for evaluation already, right?
Yes, of course. How would I think our method, right? We are not trying to say that this is the best classification or best clustering. We want to show the feature selection process. We want to say these features they affect the output.
No, that I understand, but this novelty of this Boolean polynomial means to improve and to, if you can apply, if you can improve in some dimension, and if you can apply in real time, because it is a novel approach. So if you can apply in real scenarios, then actually this theorem of the whatever you told, this model will be in use and ultimately will be in applications, right? So that's why I asked that question.
Yes.
That I got it.
We want to specify that our approach is indicative. It's not a replacement of, let's say, neural network.
No, not replacement, but it should be, we expect something more, means, something better when you are doing some research. So there should be some room to improve that.
Yes, the improvement is the indicative nature of this approach. That's what we say. Yes. Okay. Thank you.
Any more questions?
I still have one more. If no one has it.
It's all right. You can ask.
Please go ahead.
Can you please show the slide which you were talking about iris? Okay. Well,
The chat or the table?
This one, I understand. Yeah, this one.
Yeah.
So you say, do I understand correctly that you draw this separation lines using? Well, okay, the separation lines is just okay.
Yeah, we just find like which provide the best separation between the samples.
And you derive these two lines by minimizing your objective function, but actually okay.
It's like in SVC processing.
That's very.
You see, and like I highlighted here in this aggregated value, if you look, initially I had 10 different columns, but in this, this aggregation, it is indicative of I selected 7 columns instead of all the other columns, because the other columns were just adding noise. So we wanted to show that our processing is allows us to analyze this multidimensional data and actually select those features which affect our output, and then we can now use these columns and maybe train a neural network and get probably a better accuracy.
I have one more suggestion, probably your question. Have you applied your method on other tabular data sets?
Yes.
The benchmark data sets?
Not yet, not yet.
Yeah.
This result would be very interesting, because
Sure.
if you obtain such a good
I
accuracy,
invite you to collaborate with Tendai. She will be happy, and I will be as the
okay.
And
support.
what about the low clarity image and the image with noise? Have you applied on that?
Yes, for example, I think I show here this image. This is very noisy dog image here. But if you look at it, it is indicative of the actual edges, right? But of course, using a neural network, for example, right, it is now trained specifically that, okay, this is continuous grass, so consider that as a blob region. But here, our solution is indicative of there is a gradient shift here. So with further tinkering of the output, we can actually gain something. But what we want to highlight is that there are combinatorial steps that we can use for some tasks, which generally today we just have data, okay, neural network.
Any other notes, observations?
Probably during the break.
Well, I just would like to add that even the
Good afternoon, everybody. We continue, and our next speaker is Alexey Samosyuk. Alexey, are you here?
to when we try to aggregate all of this and apply it to real world examples. So those are not like that. We have simple examples in like those first 3 stages, but then we applied to modern, well, more or less around modern architectures like ResNet 50, like ShuffleNet, ResNet 200. 200 is, I would say, more or less industrial scale network, and the data sets also like MS1M, which is, I would say, academia, although there are like 60,000 classes and like 2 million classes web face. So yeah, starting with clustering. So what I mean by clustering, so we have some data, and in a very simple form, there are some features that each cluster presents. It can be represented. So if you have a matrix, you would have like blockwise matrix. And this is a very simple example, simple clustering, 3 clusters. You find relevant features, you cluster the features, and then you find like a relevant of those, and those would form like clusters, or maybe if it's a graph, it would be like eigenvectors, maybe if after PCA, regardless. So it would be something very similar to this, regardless of formal representation. So the features themselves, if you look at them, so and your data generally looks something like this. So it's a sample by feature matrix. Those or ABCDs are features and numbers are samples. So you have a distribution, like this sample has this feature, this sample has this feature, those 2 samples have like this feature, and et cetera, et cetera. And if you perform like by clustering, well, if you cluster this feature by feature matrix, it would look something like this. So there could be some feature that overlap the other features. There could be some features that are part of this. And this extends even further when you go to real world data, where I had no time to like draw this very complicated things, but overall, generally the data has more than one possible clustering, and they compete with each other. I have a better example later for that, but you have different features like semantic direction, so whatever you call this. So for it would be like colors, it could be poses, and if you try to cluster them, those are kind of mutually exclusive because the same samples want to be clustered in different ways, and then you have to somehow solve this problem. And yeah, to my knowledge, it doesn't have like ready to go solutions still, which is kind of awkward. Yeah, so this is the first part. So what I mean by clustering. Then random projection. So there is a great math. Well, we all know it. So Johnson-Richardson, we know we can, if we have, well, basically random projection, we can have, again, to simplify it, if we have a matrix, this is just Gaussian distributed matrix, we will generate it. So those vectors would be approximately orthogonal. Approximately orthogonal means if we project anything into this space, we will preserve, well, Euclidean distances, and this also has a lot of consequences. Again, not about this. So this is a part of what people use it like approximate matrix multiplication. So you have one matrix where you have like a lot of, in this case, cells. This is for biology, and I'll show because biology is a pretty good example. Because every, the initial matrix looks something like this. You can process your data in a way so it would look like this. So you would have genes, transcripts, junctions, etc., and cells. So, and each cell has its, well, those are molecules that have been captured. They're physically linearly independent because those were physically different molecules. So every number you have, like in those cells, and those genes, we know they're independent. So although they might correlate only because there's like distribution. So they coexisted in reality. In the physical world, there were those 2 together in the same cell. And this is the only reason. Well, of course, there are some technical noises, etc., but it's a good example because in this case, features are initially independent, but they're not like linearly independent mathematically. They can be correlated. So we can project this initial matrix, but again, this could be any matrix, any data. we projected by those projection vector by cell, and this matrix could be like 50,000 by 2 million by 10 million, and this way you reduce the dimensionality of the data, you get a matrix projection by genes. Projection vectors, they follow this formula, so generally you need around log n a square root of n samples to capture your distances between your samples with the I guess below like 5%. If you have some, again, there are boundary conditions and multiplicative error, not again, but so you can capture it more or less accurately. And then when you compute, you can compute some distance like cosine similarity matrix using this matrix instead of the initial. So instead of multiplying like this matrix on this matrix transposed, you can multiply this matrix by its transpose and get like approximately the same. There's like matrix that you get at this step would be approximately this one, but this matrix of projection by cell, it can be really sparse. The math tells us that there were several levels of improvement. It started from Gaussian, then there was like a Kaloptis improvement where it became binary, but then they told that you don't even need it to be binary, and now I guess the threshold is exactly at the level of like this can collect a gesture threshold like something n log n, well, some variations of log n security n, like local neighborhood aggregations, and it's pretty good. So this is very sparse matrix, this one is dense, and generally like from this approximate computation way faster than just multiplying this matrix by itself. However, instead of going to this direction, we can look at the matrix itself, like this projection vectors, and its edge case is in locality sensitive hashing, so it works the same way. So you just binarize, so each vector here could be described as a hyperplane going through your initial space, and this means that by projecting your data this way, you're just creating those cells in which you're working, and each of this cell has its index. And this is how those approximate nearest near search algorithms work. Again, they just create those cells, and then each like those samples that ended up in the same cell, they're considered their like approximate neighbors. And yeah, that's how it works. However, you can take a look at the groups of vectors, and I haven't seen many works that do that, mostly because it's pretty hard, I guess, to find which vectors should work together, as it's a high-dimensional space. But overall, using groups of vectors, the same math that works for a single sample, so you can describe a single sample with some accuracy, but you can describe any region of your space with some other, well, lower accuracy, or you can take more vectors initially and get like some threshold and accuracy, you can get it. And you can clearly see that, yeah, there is like some vectors, if you have like 1/3 of those vectors, they would correspond to like one region in the initial space, the other like group of vectors, and they would be like mutually exclusive. So when you exhausted your pool of vectors, you exhausted your initial space. So this would be like one kind of layout. Of course, there could be more fine-grained splits, and like you can take like 500 vectors in one case and like 2,000 for the other direction. But overall, you exhaust the vectors, you exhaust this kind of one directional layout. However, this is very close to the idea of clustering. So when you have cliques, you can find groups of vectors related to cliques, and then use the same, like this information that you have. So you find cliques in your data, cliques of genes, then you annotate them using these directional components. You know how do they co-align, and then you can, from those cliques, mutually independent. So you have two cliques and they mutually exclusive, negative sign between them. So you just form a full layout from them. So you can find layouts, and this is a good data set. Like this is biological data set, so it has Okay. Is it now? Does it work now? My microphone stopped working for some reason, like disconnected. When did you lose me? Hello? Here? Okay, yeah. So you can combine these clicks into using like this information, directional information into the layouts, and apparently they are meaningful. So we have the data set, like initial, like biological data set that initially had those annotations, two different types of annotation. The first one was like the cell type, and the other one was the age of this like mouse. And this is a good example of how those alternative layouts work. So the same data, so we cluster it using like, yeah, different cell types, or we can cluster it using this gradient, and they're mutually exclusive. So if you use some kind of hierarchical clustering or whatever, you will end up with something like looking like this, or with something looking like this, or any mix of that, which would be a complete mess, which is hard to work with, like really hard, because there are different groups of genes related to each. So generally, this kind of clustering would be like the best two options you have for this data set, and well, for those two specific layouts. Any intermediate cases would only like bring confusion, most likely. But again, this is a simplified example. There are more. So this is about the alternative layouts. So we can take clicks, we can take random vectors, we can form those components, we can assign those directions with the clicks, and we can generally somehow structure our high dimensional space without going into without looking at the initial like samples. But how, yeah, now to the random matrix. So those clicks in high dimensions, sorry, a little bit of PyTorch code, but yeah, sorry. So if we look at the initial vectors and the initial data is high dimensional, and there's an entire branch for vector symbolic architectures or hyperdimensional computing, where people generate like you can take initial data sets that you have, assign some random, like completely random, to generate random number driven generated vector of random numbers, and assign it to some random sample in your data, and do it for each vector for each sample in your data, and you'll end up with a matrix like samples by those random vectors. And then you can compute some relations between them. I will not talk about this because it's a really, really long story. But overall, the real data is inherently high dimensional. If you take a look at the picture, for example, you have like 3 channels, weight by height, by the quantization level of your image. So it could be like intensity from 0 to 255, or could be like larger spaces. So this is a really high dimensional space. So all of the pictures in the world that like align in this can be represented by like this 200 by 200 RGB. There has to be somewhere they have their place in this high dimensional space. It's really high dimensional. However, so if we take a look at the like simple example of how it works. So how do we form a click? So we know that every image, every initial sample, either already orthogonal just because of the high dimensionality, or it can be done orthogonal by just projecting it into this using those high dimensional vectors. So we will take this as an assumption. So the initial data is orthogonal, and we want to find relationships in this data, but there are some components of this vector that make from some directions. So if we look at some parts of those vectors, they are not so orthogonal. They might form cliques within this long vector. And generally, so this clique of orthogonal vectors form like this. You just have, is a simple example, like four vectors. If we take a mean of those, well, weighted mean, so we preserve a norm. So we would, if we aggregate like take two random vectors, two random orthogonal vectors, we take some vector in between them, so it would correlate, it would be 45 degrees from each. It would represent this hyperplane this vector now would represent a hyperplane. And at the same time, since and we can take as many vectors as we want, like 2000, whatever, it would still be a vector that would be orthogonal to the other random vectors that we have. So we are collapsing, and it would start correlating with those samples that been used during its aggregation. It's a simple idea, but it's important, kind of. Yeah, so then we go to the Gaussian matrix, how they work. So again, returning to, yeah, so this is the cliques, how they formed, and yeah, Gaussian matrix. If we take a look at the neural network and very simplified example, first we start from a linear layer. A linear layer would be a matrix E, which would be a batch matrix multiplied by the matrix of weights. And again, it's not like Gaussian, it's more like exponentially Gaussian, but we can make it work. There are a lot of papers. I cannot go into details. So let's assume for now, assume that they are Gaussian. So you just, when you multiply these matrices, you just take A times B0, A1 times B1, A2, etc. We know, so in our approximate computation, that's an interesting part. So when we perform a gradient descent, if you take a look at the sources of PyTorch, for example, they assume that this matrix follows this like Johnson-Reuschau's math. So they assume, although there's no like, I'm not sure that there is some implicit formulation for orthogonality of it, but it expected to be to work. So so forward path would be a multiplication A times B, and the reverse path, the backward path, would be multiplication B times B, which would give us an identity transform. So the entire linear encoder would work as an identity transform with this collapsed hypervectors in its like bottleneck layer over here. Yeah, so it would be like forward path and backward path. And the math here, so it just normal distribution, assume it's normal distribution, symmetric normal distribution, and it's following the same constraints. So for example, if you go into the quantization, and there are like great works, like recent works, like last year work from Amazon, like squishing weights or something, where they used, so when they conditioned their distribution from Gaussian to be like this quantized to follow this math. They didn't tell explicitly, but they follow this math. So since you know that there's no difference between this quantized matrix and Gaussian matrix from a perspective of a forward pass, it's a different story, but backward, then you can perform a weights quantization and don't lose the accuracy on a forward pass. However, so you can make a step forward, and so this is a symmetric Gaussian normal distribution. So you can just break a symmetry here. So just replace every second plus sign to the minus sign, and tell that your distribution is from 0 to x instead of from minus x to x. And this would work as a partial difference. And you can further like deconstruct this matrix into something more flatty, and you will see that this is this is just a sampling. So you're basically performing a weighted sampling, and then you perform an aggregation in it, and you can form, and depending on how you perform activation, so you take sample A with a weight B, subtract another sample with a different weight, you can get rid of samples. So and now it depends those variations of the architecture. If this is a convolutional architecture, you have this sparse field. So you can do a lot of things. So like Jacquard index would be just taking a sign of this and computing how many vectors like on the other side of it, and it would be non-symmetric Jacquard. Yeah, so it's okay. And using this formulation, so we have random sampling, of partial differences, and then we can aggregate them in different ways. So we can aggregate them like simply averaging. We can aggregate, we can take nearby samples, and this way we can describe like something like differentiation, backprop, we can describe this way. We can talk about the ordering, so we can take, instead of taking like 2 random samples, we can condition that the next sample should start in a chain, so we would do something like this. So we would connect them, and this would be a random chain again. This is and this would go to describe more correctly like ideas like bag of features, well, whatever. So again, so we have different ways of aggregating them, and we can like quantize or do not quantize them. This is about the matrix itself. Now to the network. So now when we hopefully at the same page, on the same page, there are like very well-known laws like softmax, widely used for multi-class classification. I took, well, this picture from our loss paper. I don't really distinguish them much in this, like there's no need to make any distinction. I just tell like softmax, like there are many papers on the way how you can modify softmax to, that would give you like 0.something% of improvement. But we're also doing that. And however, we're interested to make it a little bit more interpretable, because we have all of this math and networks apparently, so they do follow the same ideas, those they use the same math, they have, and but there's no good theory that would help us to describe it more like in simple terms, where we would be able to describe large networks, like real world networks, not toy examples. And so again, to simplify, we have an embedding. It passes through some network. It's just a vector with size of 1 in one dimension, 512 in the other dimension, and there are 300 of the vectors like this. This is a batch during your like backprop based algorithm. Again, they're like 4x4. Again, there's a lot of things, but we're talking about backprop based algorithm right now. And we just multiply this matrix 300 by 500 by the another matrix. In this matrix represent the dictionary, and those are like centroids of the classes. So it has like n classes. If your dataset has n classes, it could be like n people. And for real world data, this starts, I guess, from 2 million, and then it scales. Well, how many people you have in a country, that would be the number. Of course, it's not, again, there are a lot of ways to optimize this part, but we're simplifying, so it's just another huge matrix. And we can, just multiply them, dot product, one matrix by another matrix, and get another like similarity matrix, ED, that would be 300 by n. Then on average, like softmax looks like this. Margin arc phase would add some additional terms that just irrelevant now. We tried to deconstruct it into several parts that will be more interpretable, because there's a lot of things happening here. And the first thing would be the positive part of the loss, where we take our vectors, our new vectors that we have, and we want to align them. So we want to pull them closer to some other vectors that we already have in a dictionary, like to their centroids that are in a dictionary. So we have an embedding that this is a sample from a class that has to be like, this is an embedding like this dispersion shows those samples. So this sample comes to at this stage, and we want to make it as similar to this centroid as possible. This is the first part of the loss. The second part of the loss would be taking the, and this is an interesting part. So we have a temperature in softmax. If you look at the softmax, how it works, you just multiply your other vectors in the entire dictionary initially. So as how it works here. So you have a dictionary. It's like 2 million samples. You have a vector like 300. So one by for each element of in your batch, you will get a vector 1 by 2 million, and you apply a softmax with temperature, and temperatures in those cases like 60, 64 is normal. So what you end up with is like most of the data is 0 and like temperature of 64, and basically working against one sample, the closest one. And this is indeed what happens. So you're working against the closest sample. However, the samples that are those zeros, they're also important. And for some reason, I haven't seen, maybe I just haven't seen this paper, that no one tells that for contrastive learning, you need like 3 parts: positive, negative, and the basis, like this ground distribution. So you have to know how, not only where to rotate, but what to preserve. And this isn't something implicitly said, I would say. So if you reformulate a little bit this thing, so you can take only the closest vector, the closest other vector that you want to take from this like vector, and then take some random vectors, not random because they have to be the same, like that you use for positive. You're pulling towards them and you're using them as a basis for optimization. So generally you take a part of this hypercube, like 2 million vertices, hypercube, hypergraph. You take 300 nodes of it, and you're rotating those nodes, preserving the angles into the direction in a way that their relative angles will be preserved, and the angle between the closest negative pair and our positive pair would become greater. So you're just rotating the entire basis. And although this is, and we tested it, and it works for smaller networks. It works like a charm. So it gives, I don't have numbers here because there are a lot of numbers, and I'm not sure that I have to, and there's a lot of specifics because in those cases, we measure data using like TPR. So again, most of the networks in this area, like area of face rec, in this case, are like 99% accuracy. So we use a lot of different metrics to compute. So so numbers won't say much here, but the general idea, it works great for smaller networks, but for larger networks, there is one problem. So the dictionary is really large and it's not get updated fast enough. So you use only 300 vectors, then you backprop through them, which means 2 million, but 300 vectors are not getting updated. You could use a gradient for that, but you can just use a momentum. Since this thing works, you can just pull your vectors that you have, like those vectors, embedding vectors that should belong to this class. You can just update this centroid using momentum, use a local aggregation, and then update the other part using local statistics. So now all the vectors are, now the dictionary state and the network state are in sync, and you can perform updates using those like sparse updates. But this thing, and one thing I just wanted to ask this, I don't know, because this part is still confusing to us. So there is a t parameter, like this temperature parameter, and the formula, it looks like this. So you take your vector, multiply it, exponent, mean, log, but you can move this temperature out of the exponent. It would become a power of t, and this division move into the logarithm, so it would be square root of t. And this way you would get LP norm in the exponentially normalized space, but then you can just get rid of this exponent and logarithm, and still your optimization will be pretty good. So the meaningfulness of this parameter t, so you can change it like from 30 to 60 and everything would, well, the optimization would be way worse. You can lower it to 10 from 30 if 30 is optimum, and the optimization will be worse. But dropping exponent, it's just about outliers. So yeah, it's interesting part. Maybe someone can suggest.
You have used now more than 7 minutes.
Yeah. Okay, I'm finishing.
Because
So yeah, we just.
will be cut it off.
Sorry. Okay. Yeah, we just then use this idea. So if we can fix the basis, we can do it for domain adaptation, for example. So we represent one data set as like we train the network. We take this basis. We find we use the same network to find vectors that align. This would be like zero-shot learning. There's short performance. Some clusters will cluster on a new data set. We just take this new basis, and then when we perform a domain adaptation, we're not only optimizing those like distances on a new data set, but we'll also care to preserve those angles that have been on the same data set. So when we perform a rotation of this basis of a new data set, we are rotating it together. And it works. So the performance reduction, like accuracy drops, and we use a very simple loss in this test. So the accuracy of domain adaptation, so the initial was like around 9 to 11% on fine-tuning on new data. Then after this step, so we don't use the data from the previous domain, only the model and the dictionary, and it's enough to preserve the quality. And we can also do a lot of quite amazing things, especially when the data set gets bigger. There are a lot more relationships, and you can also describe them in the same terms, and it works. We also have post-training regularization technique. We found later when we finished this that like the same year, I guess, Google published a very similar idea, a lot of similar ideas here. And the idea, we can use the noise to tune the network, like to spread this vectors, those centroids a little bit, so there would be not an empty space between them. So to form an empty space, you need something in this, like between them. So you can just add random data just out of the domain, like ImageNet or something else. But if you take the same data set and blur it and try to use it for regularization, it wouldn't work. We published it. It's now, and we will update this library like OpenMetas to add some additional techniques based on those ideas. And yeah, we'll continue working, like hopefully maybe someone can help with some papers, some like especially regarding this p-norms and fractional norms, something that help us understand them better. And there's a lot more, but yeah, I don't have time, only 20 minutes already out of time. So hopefully it was clear enough. Thank you.
Work and very helpful advices just about this work, about presentation of this work. So I will start. Perhaps it's possible to see only my publication, but of course in the text in article there are many, there are not very, but there are several quotation of several links to other publication to this field. What can I say about this field? About the structure of this presentation, just a moment. It consists of two parts. The first part concerns only classification problem, graph decomposition only. And this idea, very old idea for me, about 20 years, but I suggested firstly, we can say that, thought up about it, and it has several applications. For instance, in political bodies, in image processing, and in the stock market. Just this presentation is devoted only to application in stock market. But first of all, I would like to present the idea of decomposition that is simple enough, but however, it's strong enough, I venture to say about myself. What means graph decomposition? It's clear that if you have a graph, you would like to find some subset of his vertices, so that in relatively few connections between these parts and relatively many connections inside. It's clear. It's not formal definition, of course, but it's clear what's the problem. So however, just a moment, I can see oil. It's very easy for me. You will see the same. A moment. It's clear. So what is three parts of this part? Notion definition, algorithm itself, and numerical characteristics. Perhaps very sometimes useful. What's partition? First of all, from the advice, I can say, advice of Mirkin, give exact, no, not exact, but give definition of all the main notions. So partition, it's clear what's partition. Graph decomposition is family of subgraphs, and so on. It's also clear what it is. Graph dichotomy is graph decomposition into two subgraphs. And graph depth, what?
Another slide.
Here, understood. It's possible without it. Well, I see. Much easier. Well, as next one, graph decomposition, partition, and especially graph depth. It's a new characteristic of graph entanglement. Steppency graph. Calculated the further described algorithm of family of dichotomies contraction. So what about it? Like many other algorithms, it consists of two parts: initialization stage and regular stage, that is repeated several times. It's also parameter. First of all, what's initialization? Initial assignment necessary parameters. A random value from 1 to 5 till 5. It's 5 is just one of parameters from the algorithm. It can be 1 till 1, also possible 1 till 10. It's not so important. I defined an initial loading in all the edges of the given graph. What is named loading? Perhaps the most important, very important notion in this report. And it's really a maximum. It's a maximum. Maximum of edge loading is defined as the initial maximum loading. It will be described early, and initial value d is 0, and number execution of regular stage is t. Well, the next one. Initial assignments. It already was. At every execution of regular stage, there are several input data. Some input data, graph itself never changes, current value of loading in all the edges, current value of maximum loading, and maximum it's taking over over all the edges, and current value of graph depth. After every execution of the regular stage, produce modified values of loading in all the edges, modified value of graph depth, modified value of depth, current depth, Lmax, and one dichotomy is constructed. But every regular stage produces one new dichotomy. So, what's regular stage? Perhaps this algorithm will be illustrated by a picture, but however now it's not so. Of course, only main page, main steps are described without I omit many details, of course. choose a random a pair of different vertices from the set of vertices. V, it's clear. Not clear, it's not clear, but it's the most important step here. It's the second step. Construct a minimum path connecting the two chosen vertices by Dijkstra algorithm. But the length of an edge is current loading. The length of a path is equal to the length of its longest edge, not the sum, but the maximal. It's also very known notion, and of course, Dijkstra algorithm works in this situation also with maximum. And what after the deal? After we selected constructed, not we, Dijkstra algorithm constructed one path, it increased by 1 all the current loading and all the edges, because this path just go along all these edges. So loading is increased by 1 and increase by 1 the current value of graph depth. It means any path increases value of depth of the graph by 1. And execute steps 1 to 4 till the maximum value of loading exceeds the current value L max. Consider the initial graph with the loading just before the finding this path. The set of edges whose loading is equal to L max contain some cut. This graph is from after that we can, by deletion of this all these edges, we construct the number of components becomes more than 1. Perhaps not compulsory 2, perhaps more. But and we construct two subgraph, one with a maximum number of vertices as a union all the other component. Of course, really it's described how to unite all the others and so on. It's of course, but really what's important, it's all virtual operation, I can say, because graph all the time is the same. Now loading of edges of course changes. The length also, so-called depth of graph also changed, but also only increasing. But the graph all the time is the same. I would like to show in the picture because it's much easy to understand because it's central part. What means there are 3 cases of regular stages. Case A, both line is just edges with maximum loading. In all the other edges, loading is less. If they do not form any cut, they don't contain any cut, so you can take arbitrary vertices A and B and find the path, shortest path. Of course, the shortest path, because of his minimax definition, he never go through along these edges with maximum loading, because he tried 5 because it's, he tries to find a path with minimal length. A length of the path is the maximal value of length of any edges. From this, in this possible find. Case B, all these edges with maximum loading do contain some cut of the graph, but if vertices A and B from one side of this, inside of one of component of connectivity component of the graph, it's so possible also find this. Let me show something here. How to show something. Do you have something to show? Можешь показать что-то здесь или там? Вот показать место. Where it is? Вот это?
Все, попробуйте.
No, it's not so well. So. Есть вроде курсора. Здесь нет его курсора. А куда он делся?
Нет, нажимайте, и он будет показывать.
Well, the most interesting the case C was here. It's the case where all the set of edges with maximal loading do contain, like in case B, do contain some cut of the graph, but A and B as different components of this graph. So from this, any path, including shortest path, must go through at least one, but really along one of these edges, because we increase any loading by one, we will increase maximal value L maximum. It also will increase by one. So, and we go to the, first of all, from this previous step, we find some dichotomy. Not find, it's clear, it's given after elimination, even virtual of these edges. And so we can go to the next stage, to the next regular stage. What will happen after all of them? So how to construct algorithm? It's only one dichotomy in two parts, but how to construct dichotomy to many parts? To many parts. It's very natural, because the first it select one component, one subgraph, and after it apply the same. But we select this algorithm select a subgraph with maximum number of vertices. And afterwards, the same algorithm is used another time for this subgraph, the same algorithm, and so on, find dichotomy, and afterwards, from all the pair of found subgraphs, select the one whose maximal number of vertices in both subgraphs is the minimal among all the pair. And what I mean here? Well, that's okay. Replace the selected subgraph with two found and previous step and the previous step 3, and we find the composition into k plus 1 subgraph. So we must, in the beginning, we have some required number g of subgraphs, and we can construct subgraph decomposition into g subgraphs. What necessary to say here, to say about all these constructions? It's very simple construction, but it is effective. Why? I can say practically is all the, I know of course a lot of methods of classification of graph decomposition, and in any methods the goal of any method is to find some decomposition, the best decomposition. It's so possible if the graph is simple, a simple one, any many methods will find the same. But if you have some more complicated situation, I can say perhaps to sharp the best, or not the best, the correct decomposition simply does not exist. No, not at all. You can construct because I use random generator in all this construction. You can find many different decompositions. Many different. No, if I repeat this 1,000 times, but typically 30 or 500 of vertices. 30, 40, 20, something like this. Not 100, but number of different dichotomy. And after that, one dichotomy is selected. Because you have a lot, you can select one. In many cases, not necessary to select one. It's also exists, but it's not in this work, some I can say some characteristic of the graph itself that is defined following this all these different decompositions. It's called like entropy of this family of decompositions, of different decompositions, different dichotomies. So, what is necessary to add? All this construction need only graph, and no metric information is used here. But typically, in many problems, you have metric, you have distance between objects, between elements. And so, of course, it's possible not only to construct graph. Typically, I take 4 closest, and so consider this graph, after that find the composition of the graph. But when you select one, the composition among many, it's possible also use metric distances between elements, and from that I used just in the market, in stock market, it's because I have prices from time, and finally I have distance between different objects, because it's time, it's prices during 15 days. Also parameter, my parameter, I will explain all parameter after that. And so it's possible to use not only in such case it's possible to use not only graph characteristic itself, graph only, but also metrics. So what I do, I find average distance between all elements in one subgraph, and into subgraph of the composition, I select one, I select pair, one decomposition, one dichotomy, where the maximum, where this number of vertices will be minimal among these two. It will be minimum, maximal of two graph, maximum number of vertices in both graph, both part of the dichotomy, or the all thousand, perhaps of course less, but all thousand variant will be minimal. It's I can say tend to situation excluding such that you have 1000, you have 500 vertices, you have 495 and 5. I try to excluding if a normal, I guess, uniform decomposition exists, it will be found by this algorithm. But if also it's possible in this place use the second part, the same algorithm, but not instead of number of elements, you can consider average distance between all the elements in this subgraph. It must be, of course, when less, when better. Its distance must be maybe as close to one to other as possible. The same, it's selected one of two, which has the worst case, and afterwards all the pair, algorithm selects this one with maximal possible density. Density is clear, it's something like distance, but when more and better. So this is end of the first part of my presentation. Second part concern just a moment, I can do it. So modified algorithm that I told just now of these things. And finally, second part of my presentation concerns just market graphs for S&P 500. It's a very popular object because 500 not a lot, but of course it's 500 largest or greatest American companies, and from that, of course, it's I can say behavior of this market. It's very typical for all the economic, not only the United States. So what's written? Some standard conditions. So I consider 15 days, L here 15, price of share. So consider with these days, all the information is related to the last day. It's clear. And also distance, it's clear. Distance is defined by correlation coefficient. It's standard things. This construction, I can say, a very known contraction. Only one thing, because sometimes not with some number of closed, but in many construction multigraph, consider it's a level of coefficient correlation coefficient is given, function 0.6 and of 0.7, and as connected only with pair whose coefficient is more than this number. But I prefer, because sometimes it's not uniform in a different part of this graph. Distance can be scientifically be different. I mean, coefficient of correlation. From that, I prefer take a fixed number. Why for? Like all the other parameters will be explained for all of them. Custom graph is called the market graph. It's a very known notion for more than 20 years, perhaps even more. I have, of course, link to on the first work about it. General scheme of the daily trading algorithm. What's so about? Many people try to predict big crisis. I don't engage at all in this problem. I think only about trading the next day, using formation of the previous day. Like not only me, we have a lot of publication concerning the same problem. What to do the next day? Which shares to buy, which share to sell. Of course, in this point of view, it's standard things. But how to do it? It's the approach is very known, but how to do it is different things. So the second point, it's a general scheme. Building graph of share on the base of this analysis, which is advisable to trade the next day, or decide to skip trading the next day. Sometimes also necessary to skip the next day if you know perhaps bad results. But pay attention, the item 4, making decision about suspension of trading for a certain period, not for one day, and not because it can be something bad, not because it's this decision depends on the result achieved during the previous period. Result can be good, not only bad. Good results and have bad results. In both cases, we stop the trading up to end of period. Connected period is 1 quarter, about 62, 63 working days. So I considered 21 years, 84 period, 84 quarters between 1990 and 2010. Big rise just inside this period, but it's not so important. For me, big rise is not so important. I will explain what it means. So, for the previous day. Well, very simple idea here. I consider I can say market graph constructed for last day, for today, in the evening, and the previous day. So in both graphs, I construct decomposition into 12. It's not so important. In 12, also parameter. In 12 subgraphs, I can say cluster and what is perhaps something new, not so new, but I found the maximum intersection of the cluster, maximum number of elements. So we have two clusters, the same set, of course, but with big in this intersection, you have share that have similar, because we're inside one classes. We have, I can say, similar behavior in last 15 days. What does it mean? The next choice, it's like, because after that, just the end here, find subset, so it's some other condition. So for M, if we say to field M, whose cost increased from yesterday and denote with an M plus, and here and whose cost decreased from yesterday, it's denote a M minus. So of course it's natural idea to suppose that this chair the next day, but a known day, next day, tomorrow, you have the same behavior. But of course it's not a fact. Moreover, I think what to do is not so. We will just know what's possible to do about it. In many cases it's so, but not always. I can say it's not always so. Very simple recommendation, of course, for share from graph for the group M minus. Of course, the next day proposed to sell this share at the price at the market opening, which is assumed to be close to the price at the closer time as the day before, and so buy at the market closer time the price, because it will be cheaper. And the same M plus, it will be this day is helpful to to buy one share and sell it then was then the end of this day, but in the morning to buy, and so because in this part price increases. So it's a very natural idea, but why it can work? Because I used not only this fact from last 2 days, but also from previous 15 days. From that, very often give good results, but not often. But what after that? What is really new thing I can say? Stopping rule. The considered elementary periods one quarter, and SOT is a cumulative income after day t from the beginning of the considered quarter. The first day is 0, but I use day 0, day 1 I use only to predict the next, not to predict to consider the next day, and so on. So what is the idea here? I define two numbers, two threshold, one negative minus 25 and positive plus 50. So I make a decision every day. Is cumulative income. It means from the beginning of quarter up to this day. It's good enough. It's not good. Also, a trading is suspended till the end of the current quarter. Is income more than 50? When a trading is suspended, it's a good result. So you can some money, and so not to play more. So otherwise, the above described trading algorithm continue to work. Of course, this algorithm can be named, but it's really so caution algorithm. Осторожный. I can say even трусливый. That's so. So I can tell the very known Russian expression in Russian, but explain its meaning. Не за то отец сына бил, что тот играл, за то, что отыгрался. Main idea here, you must be satisfied with not big but positive result. That's all. It's very known. It's also known idea. By the way, this situation a bit similar, not a lot, but a bit similar to very known problem, secretary problem, because you also must finish. You don't know what will be after that. But in this case, you have probability. But here you know nothing. And however, you can make reasonable decision. Why reasonable? After that, I can present some table. That's all. Result of the stopping rule. It's 3 period, 3 quarter. Not up to the end. It's but it's clear what happened. And the place where I stop. Oi, why it not this place? Something happened here. Something happened here. Что-то съехали вот эти черненькие-то мои. Съехали, они у меня были по-другому расположены. Они были тоже наверху, но были по-другому. Well, what we can see here. Anyway, it's possible to... А может, еще раз выключить и включить эту картинку, показать. У меня она, так сказать... Все, время уже нет. Все, that's okay. That's okay. So, what's clear from here? Several quarters, between 41, oh, 40, between 40, because 10 years, 20 years, 21 years, 81. 81. Well, and we can what hit here negative result, we stop here. 29 minus. Here also negative result, and we stop just here. Here positive result, and we stop here. More than 50. The same is here. Pay attention. The same is here. And the same is here. Pay attention here. Also be I know picture is spoiled, but I don't know why. It's important. From that, by the pay attention, is just period before Great Crisis. It's third quarter of 2008. But I don't consider here you can receive much more. Here you can receive also no less. Here also can receive more here and so on. But I stop. It's stopping rule. The stopping rule. So what after that? It's almost all. I calculate this algorithm from 20 years, 21 year. You can hear annual income, sometimes negative. It's cumulative income and sum. You can see some increase anyway, and it's possible to see better presentation here. It's a regression line, its results here, income here, time. You can see, moreover, I can say that I contract, I calculate many such, perhaps 3 or 4 such pictures, or some of them up to 2019. The character was the same. Sometimes I change some not important details, but anyway, result is the same. It's positive result. What can be said about it? Result itself not so good. Very little sum, but a little sum. For instance, $2,000 so on for many years. But first of all, I buy one. I deal with one share, only one share. If you do the same with 100 share, we will receive 100 times. So in 1,000 share, we will receive 1,000 times more when written here. When it's not so bad result. But of course, what I would like only to before to start to end, parameters. We suggest algorithm is the algorithm of data analysis, and it is not an algorithm of stock market imitation. No assumption about stock market behavior itself as well as about behavior of the actor. No probabilistic, no any assumption at all. I consider data as a fixed number. But I know, and I don't suppose anything about them, anything. It's only, but when I produce, I use probability, like because I use random standard dimensionality, but something else, because in this case it's possible to use limit theorem and so on. Not as possible to use to initial data is that absolutely unknown. I think all of us understand the difference between what is unknown, with uncertainty and probability. Very different things. So I support only uncertainty, not probability at all. And after that, there is several things how to improve this algorithm. Of course, there are many ways to improve it. I don't intend to. Of course, I would like to underline that's not the end of the work. It's a beginning of the work. Serious analysis of fund, because not only this stock market, also the others, but I can say it's necessary to understand, pay attention, that big crisis don't, I can say it, don't trouble me. Do not trouble me at all. You receive plus even before this crisis. And even after that, of course. It's because as idea, of course, of this. And the last picture, no, don't worry, is the last about Great Crash. Some people can consider that it's absolutely Monte Carlo, nothing to do. Great Crash to 1929. It's a citation of Moim, The Razor's Edge. My friends at Vatican told me that the crash with coming and strong advised me to sell all my American securities. The Catholic Church has a wisdom of 20 centuries behind it. I didn't hesitate for a moment. So when the crash comes, you were sitting pretty. Вуз не дули in Russian is written. I have also the Russian. I have to show just the Russian text also. Вы в ус не дули. Не знаю, зачем понадобилось употреблять эти вульгарные выражения, но смысл прошедшего он довольно точный. Я ничего не потерял. Мало того, сорвал, как вы, вероятно, выразились, изрядный куш. So the answer to people that... That's all. That's all. Не, ну не 15. Да, тоже смотрел на часы. Не 15. 5 минут. 5. 5. That's all. That's all. Of course.
Alright, the first one is that generally when you propose a strategy, a trading strategy, you compare it to some other strategies.
Of course, I have compared.
The performance of the index, such as S&P 500, or perhaps such strategies as quantitative traded, etc. Could you clarify how your strategy compares to the performance of the index over this period?
Index, it's not a result. Index, it's a parameter of market itself. Result is money that people can earn.
Yes, just suppose that you invested the same money as in your strategy, but in the index. They used to compare.
No, I don't compare with index.
Yeah, just I think that it would be a good idea to try it.
Perhaps a lot of ideas to try. First of all, how to earn more. I know several ways. By the way, I wrote myself all the program, and a lot of technical work here. You understand? Here really 5 or 6 programs, really different. But not, there are many possibilities to improve this result. Of course, I saw the previous things, and I can say only one thing, but they all are not stable, I can say. And this is stable, really, in mathematical sense.
I think there is actually some sort of metric to measure the stability of your strategy.
Because I can do not this one times. Really I did 5 times, but it's possible to do 50 times because it's soon enough. It's possible to do, and so. But it's really after. It's not initial data. It's a product. It's a result of its processing. It is really result is really random value in mathematical sense. From that you can use. Of course, in some days can be negative, but some days more days more positive, and from that you have good sum, positive sum. That's all.
And another question. We talked about cuts and flows. How does your algorithm correspond to the Ford and Fulkerson algorithm?
No, of course, I know very well this.
Yeah, just it seems that there is some sort of similarity.
But no, it's not. It's not, because I know this set of edges, this whose loading, you can length, I can say anyway, any parameter is equal, maximal equal, all the cut. We have more, but it contains cut. From that I simply eliminate all this. I don't need to find it. My algorithm finds all this loading, and including the fact that loading is maximal one. And so I don't need to find this, like in Ford Wilkerson, find this, especially find this cut. It's just is found by the algorithm itself, by my algorithm. And after that I simply eliminate, not I can say virtually eliminate for some time. I don't change graph itself after that. And that's I understand your question, but it's not a problem at all. We know these edges. By this pay that I do it several times, just a moment when it's increases in 1. Its maximal load increases with 1, because it's only calculation, not nothing due to this graph itself.
I think that you can probably say that your algorithm is a modification of Fulkerson.
Not, because I use absolutely other. I use idea that I find 2 vertices, and by Dijkstra, minimax variant of Dijkstra finds all what necessary. It's, I can say, the first idea of all this many years ago. But this idea works also in political bodies, also in image processing, many cases.
Any more questions? Thank you very much. So our next speaker is Susana Nascimento.
To start anyway.
Susana, do you hear me? It's Boris speaking. Do you hear me, Susana?
Good afternoon, everyone, and thank you very much for this invitation to participate in the international conference dedicated to the 18th birthday of Professor Boris Mirkin. So this work is entitled a 3-stage cluster modeling for the spatial temporal analysis of CoastalUpwelling. And this is a joint work with my former student Alexandre Martins, colleagues Paulo Relvas and Joaquim Luís from University of Algarve in the field of oceanography, and Boris Mirkin, that deserves any presentation. Okay, the CoastalUpwelling event is an ocean dynamic phenomena that manifests by cold, less salting and nutrient-rich waters. It occurs by the combined effect of the wind stress over the coastal oceanic waters and the Coriolis force, causing the surface waters to move away from the coast. And it has important implications lie in the study of the ocean dynamics, to understand climate models, and on fisheries. So there are huge amounts of sea surface temperature images available for over 40 years from the advanced very high resolution radiometer sensor on the board of NOAA satellite. And the oceanographers has two main goals in mind: to automatically segment the coastal upwelling regions that are characterized by relatively narrow region with a relatively strong horizontal thermal gradients to the coastline, and also to analyze the spatial temporal tracking of the upwelling to identify trends along the years. So some challenges concerning this problem is that the analysis of the sea surface temperature images along time show patterns that change their shape, the size, location, and every very distinct scales in space and in time. There is also the absence of reliable ground truth maps. So according to this, it demands the extraction of appropriate features to overcome the semantic gap between the upwelling pattern expressed on SCSTs and the physical model underlying the phenomenon. And we empirically observed that. Yes, Boris?
Susana, switch on the presentation. We see your face, not presentation.
Oh, I'm sorry. Many thanks, many thanks.
Please.
Is it okay right now?
Yes.
I'm sorry. I'm so sorry because if you allow me, I'm going to leave and come in again on the session because I'm not able to hear myself. What should I do? I'm not able to hearing anyone.
We can hear you.
Yes, Boris.
Susana, we can hear you in the video. Just continue and again switch on your presentation.
Yeah.
I see your face, but not the
presentation. But
switch on and continue.
Okay, I'm going to continue, and I'm sorry for this because
it's not you,
I don't know what's.
And they should be sorry because.
Don't worry,
technical.
don't worry,
okay.
Don't worry. Okay, bye. So as I was saying, we empirically observed that each early upwelling season can be divided into shorter periods at which the upwelling shape is more or less constant. So in this way, we propose the three-stage clustering approach. On the first, we segment the sea surface temperature grids derived from the satellite images to extract the upwelling regions. Then we find the upwelling time ranges as periods of stability. And finally, we find a core shell cluster within those time ranges. So the first method and model is for the segmentation we developed a couple of years ago with the self-tuning expanding cluster algorithm. Given a preprocessed SST grid with temperature values measured Aij at each pixel Ij, we consider a model by following the approximation clustering model by Mirkin 1996, in such a way that each observed temperature value can be approximated as the product of an unknown cluster intensity and a known cluster membership Gij plus a residual value Eij to be found. And to optimize this model, we consider a least squares clustering criterion, minimizing the square of residual values for the unknown cluster intensities, then the unknown cluster memberships to be found. And we easily can derive that the intensities will be nothing else than the mean temperatures of the pixels belonging to the cluster. So I don't have time to go into details of the iterative algorithm we had developed for this model, but we can say that the self-tuning self algorithm extends the popular seed region growing for image segmentation via the approximation clustering in the following aspects. The clustering criterion takes the format of a product rather than the conventional difference. The cluster expands through a homogeneity threshold adaptively optimized from the clustering criterion. The cluster expands over a window serving as a boundary regularizer, and in such a way, no order dependence of the pixel testing to be labeled is required. So in these figures, we can see, we illustrate the kind of segmentation results we obtain with the STSEC algorithm. For the case of the Portuguese coast, where we have on the left a sea surface temperature image, in the middle this image after a pre-processing stage where we highlight the coastal upwelling region, and on the right the binary map obtained by STSEC algorithm where the upwelling region is highlighted in green. And the same, another example, when applied to the region of the Atlantic Ocean of North Africa. At the second stage, we want to find time ranges along consecutive SST images. So in fact, the upwelling does not gradually evolve through time, but instead it presents several time segments where the events shown similar behaviors. To accomplish that, we start extracting 4 features from the STSEC segmentations: the total area of the upwelling region, the average temperature over the upwelling pattern, and the maximum and the minimum latitudes of the upwelling regions. And with that, we want to cluster consecutive SCST grids. So for that, we had adopted the iterative anomalous pattern algorithm proposed by Mirkin, originally as an intelligent initialization for the popular K-means algorithm. The iterative anomalous pattern algorithm sequentially extracts clusters one by one and allows to model the number of clusters in an unsupervised way. In our case, we had explored this algorithm for the unsupervised segmentation of time series, and so we ran the EAP taking as input the 4 features extracted from the STSEC segmentations and derived automatically in an unsupervised way by modeling its top condition, the number of time ranges. So in this table, we illustrate the forming time ranges for 3 independent upwelling seasons of the Portuguese coast. And it's very much interesting because those number of upwelling time ranges is consistently for each year between 3 and 5 for both collections of SCST data in different regions of the world, the Portuguese coast and the Atlantic of North Africa. On the final stage, we want to find a core shell cluster to represent the time ranges as a piecewise constant model of the upwelling. So, and for this, we again consider a given preprocessed SST grid A as a matrix AT of Ij with temperature values Ij of T. A core shell cluster U is a sequence of T cluster slices R union ST equal 1 till R union ST equal T capital, with T capital previously derived from the iterative anomalous pattern algorithm, and with R a constant set, the core, and S of T a variable set, the shell, at each moment T, not overlapping R. So a core shell cluster slice is represented by two non-overlapping sets, R union S of T, with binary values Rij belonging to the core and Sij of T belonging to the shell, such that their product is equal to 0. The model to represent an upwelling SST at pixel Ij and moment T is approximated by the sum of the pixels belonging to the core plus the pixels belonging to the shell, weighted by values that corresponding to the intensities of the core and of the shells and are to be found, and plus a small residual value Eij. Again, the residual values are minimizing according to the least squares clustering criterion defined by this equation 6, and it's not difficult to derive that the first order minimality conditions of this function delta, the clustering criterion at moment T, lead to intensity values for the core and the shells that lambda and lambda plus mu that are nothing else than the mean temperatures of the pixels belonging to each part of the core shell cluster. Criterion delta can be rewritten as the difference of a portion D that is defined as the total data scatter, and that is constant for our data, and G that is the core shell cluster's contribution to that and is to be maximized. Okay, so and to maximize this portion G, we proposed an iterative algorithm. The input is a collection of T SST grids, and the output is one core shell cluster that is a sequence of T cluster slices and the corresponding intensity values lambda of T and lambda of T plus mu of T. At the initialization of the algorithm, we run the sequential self-tuning algorithm over each SST grid AT and let C1, C2, and CT be the obtaining upwelling regions. We calculate the initial core as the intersection of those clusters and the corresponding shells, the set difference of the cluster minus the core. And then we define a set B as the union of the core and the set of the shells, and another set F defined by the grid points forming a four neighborhood with the region defined by the core and the collection of the cells. And we calculate the intensity values of core and shells previously defined. So at the iterative step of the algorithm, for each pixel Ij belonging to set B, we want to decide which scenario to take, or to make the point Ij to belong to the core, or to make Ij to belong to any of the T shells, or to remove the point to any of them. And we take the option that makes the increase of criterion G. And this process iterates until there is no improvement in the criterion we are maximizing. So in this figure, we illustrate the structure of the core shell clustering algorithm for an example of a time range forming by 5 consecutive sea surface temperature maps on the top after being pre-processed. In the row in the middle, it's the result of having applied the ST-sec algorithm and finding the upwelling regions marked in green. And from there, we defined the initial core shell clustering. And at the end, in the last row, we can see the core shell clustering result with the constant core highlighted in yellow and the dynamic part, the shells in green. So this is the entire architecture of this 3-stage clustering. I'm not going into details on that. And now moving to analysis of the time series. So we had taken 2 annual collections of sea surface temperature grids derived from the satellite images corresponding to 16 years each, 2004 to 2019, and covering the Portuguese coast and the Atlantic Ocean of North Africa. Each SCST grid corresponds and is represented to the average of 8 days of each. So first we start accessing the results of the core cell clustering segmentations. And for that, we are taking as ground truth the segmentations obtained by the self-tuning set algorithm. In fact, the segmentations obtained by this algorithm constitute reliable ground truth maps since they obtained very good evaluation scores when validated by a team of expert oceanographers. Even so, we had applied the Rubchinsky similarity index to measure the concordance between the core shell cluster and the ST-sec segmentation results, and we obtained it for a relatively diverse sample of images, similarity scores higher or equal 0.98 out of 1. So to make the interannual time series analysis, we consider several features: the areas of the cores and the areas of the shells forming the core shell clusters, the average temperature of each of these structures that are nothing else than the intensities deriving by the core shell clustering algorithm, and the average temperature of the upwelling core against the average temperature of the offshore ocean waters. To illustrate, we show in this graphic the comparison of the average core temperatures against the temperatures of the offshore waters in the Portuguese coast for the year 2015. And interestingly, the maximum average temperature of the core occurs at the middle of the upwelling season, and the maximum temperature of the difference between the core and the offshore waters is very close by. We obtain concordant results for all years, and this shows that the upwelling events tend to increase in the summer season, where the coastal upwelling tend to have its strongest activity. Analyzing these results in the interannual time series, we can see that along the 16 years, we can see that the core's temperatures are consistently lower than the offshore ones, reflecting the permanent upwelling regions close to the coast and captured by the analysis of the core structures. On the other end, the annual cycle of SCST is observed both in the cores and the offshores, but the differences between the core and the offshore temperatures are stronger again during the summer months that correspond in fact to the peak of the upwelling and is consistent with the upwelling regime. Looking at the areas of the cores, the shells, and the core shell cluster against the areas of the whole upwelling regions obtained by the self-tuning sec, we again see that the cores are constant structures along each of the four upwelling time ranges previously determined, that in here are in the number of 4 in the orange line, the shells in the green line corresponds the evolving spatial pattern strongly concordant with the evolving areas of the whole upwelling region of the original STSEC algorithm. Now, looking at the entire picture of the interannual time series, we can, along the 16 years, we can see that the coastal areas occupied by the cold upwelling authors have been increasing along those 16 years under analysis, and the increased extent of the surface signal of the upwelling is in fact the manifestation of an increase of the upwelling intensity and or the increase of the cyclonic wind stress curve along the coast. So, as conclusion, a novel approach for the automatic recognition of spatial temporal analysis of coastal upwelling is proposed. It consists of a 3-stage clustering based on Mirkin's data recovering approach, the STSEC clustering to segment the upwelling grids at each image, the iterative anomalous pattern for an unsupervised segmentation of the time series to find the time ranges, the core shell clustering to determine the piecewise constant model of the upwelling within those time ranges. So the 3 clustering models stand on the least squares minimization of the corresponding clustering criterion and allow to derive key parameters of the models in an automated way. We have applied this framework to real-world sea surface temperature data covering 2 distinct regions of the world, and the time series of the upwelling features present consistent regularities among several independent upwelling seasons, as validated by the expert oceanographers. So, and I should say, thank you very much, Boris, for having introduced me and my colleagues here in Portugal to the clustering within the data recovery paradigm. Okay, thank you very much for your attention.
Any questions? We have a...
Just curious, how is this data further used? Like, what are the purposes like later on? This is like very massive research.
Она, по-моему, не слышит. Так что, Борис Григорьевич, поблагодарите ее за замечательный доклад, потому что мы ничего не можем сделать. And I'm announcing the next speaker is Dr. Frolov.
Hello everyone, my name is Dmitry, and I would like to present you a 3-step method for audience extension in internet advertising using an industrial taxonomy. The work was prepared by Dmitry Frolov, who is the presenter, and Zina Taran. The affiliations are for me is HSC University during the work of on this direction, and currently I'm working in Light MPI. First of all, I will touch programmatic digital advertising overall. We'll briefly describe targeting strategies and insufficient audience problem. After that, move to taxonomies and generalization, and our method to work with this issue, and describe our LUSP method for audience extension. After that, we'll conclude the results. First of all, I would like to tell a bit about programmatic digital advertising. Now they see the common tendency of moving advertising from conventional formats such as TV, radio, and others to the internet, because this new way allows to have a lot of advantages. First of all, investigate potential audience way better, create and control advertisements of different types, evaluate the results, because, for example, if we will consider TV advertising, we know we have a well-known issue with controllability of this. It's quite hard to evaluate the results of advertising, especially for small audience. And programmatic is one of the most popular modern approaches based on buying user contacts in a real-time auction instead of buying some places somewhere. And RTB, that is real-time bidding, is a common technique to implement this approach, and it's based on buying contacts with user. Say I have user visiting some site, I can buy the opportunity to show something to this user. And typically to describe users and segments, we have user segments that are user interests determined from the information that we know about the user, such as visited websites, opened pages, read history, and similar things. And the same we have for advertising campaigns. They also can be described in terms of segments. And overall, these things can be referred as users' profiles. For example, here you can see one such small profile, Volvo Cars owner and businessman. So there are also common well-known issues with this approach. Sorry. First of all, this is insufficient information about the user when it's difficult to make a decision, should we show something to this user or not. This is the reason for that can be, for example, we have only restricted access to the user history. For example, one page in his history of visits in the internet, and of course it's very hard to analyze user interests from that. The second thing is extremely large volumes of data, and this is especially important for small technological companies. So sometimes instead of analyzing the content of a web page, companies analyze only the URL of the page because it's very hard to analyze each individual page. So and due to that, of course, we can have issues with quality of such kind of analysis. Also, next thing is technical problems with bidders. It's very important to respond quickly because the time when user is taking a look at the web page is very limited, and we should make the bids, and we should make decisions very quickly, as fast as it's possible. Typically, the command limit for client-server interaction in these cases is 100 milliseconds. That means that all the bidders behind the hood for auction systems should communicate and respond in just 100 milliseconds. Also, the important problem is bots and fraud traffic. This is continuing fight of defense and attack, and there is a chance to pay for a bot instead of a real user, and companies make many attempts to develop techniques how to defeat this problem. And the issue that I would like to emphasize is insufficient audience for some campaigns. This is especially important for small technological companies, and I had some experience of working in such a company. And for some companies, the audience size defined by initial segments and initial user profiles is extremely small. That means that if we have a company that would like to buy advertising, it's in some cases such companies are just unavailable to gather these requirements, to provide a sufficient amount of users who see the advertisements and make some actions, like go to a website by a click on advertising and things like that. So let me briefly describe common techniques of targeting in programmatic. Typically, conventional approach I will naming it CAS. This is conventional selection of a targeted audience, and the rule is the following: for a given set of segments provided by advertiser and user profile, just check whether the profile has one or more of advertisers' marketing segments. So typically we pre-specify some threshold T as some value, and the user is selected as a part of target audience if at least one of the segments has weights greater than T, according to the this CAS rule. And this is a pretty straightforward technique. It requires, of course, that we should pre-classify the user and derive user segments for user, and obtain belongings values for audience. And the issue here, of course, is a small audience and the limited opportunity to control the size of the audience. And the common way that can be used here is just to lessen the belongingness value, of course. So we will definitely get more users than initially, but of course the quality of this new audience can be significantly lower than quality of initial audience. And the question here is maybe we can invent more efficient solution with these segments. And yes, we can. The idea is use industrial taxonomy, and I will describe here the most famous IAB content taxonomy. IAB is Internet Advertising Bureau. This is a worldwide organization that specifies and supports standards and protocols in the area of internet advertising, and they have their own user interest taxonomy that contains more than 1,000 different segments arranged in the taxonomy tree. And the idea of our approach is to generalize low-level user segments to get accurate, this is very important, high-level segments and use them for targeting. So the idea I will describe here, the core thing is generalization of user segments. So in this context, we define generalization as appropriate lifting of topics to common root concepts. And here you can see a small example. Say we have the initial set A1, A2, A3, A4, and B1, and we can lift this initial set of leaves to higher rank node A, and in this case B1 will be disregarded as an offshoot. And let us take a look at this approach more closely. We can have different alternatives when we consider generalization, and in say we have one more example. Here you can see the leaves that are colored as black, and the option to lift in this segment of taxonomy 3 is to lift the initial set, these nodes, to the root of the tree, to the head subject A. And in that case, we will have the we will also cover by our head subject those leaves that will not belong to the initial set, but we still have them in the new head subject. This is the first option. And the second option is just to lift the initial set to the root of the left subtree. And in this case, as you see, we have one gap and one offshoot. And how to decide what option will be better? Our method is lift to minimize the penalty. And we assign the penalty for each option as a weighted sum of number of head subjects plus lambda multiplied by number of gaps plus gamma multiplied by a number of offshoots. And this algorithm was introduced by Boris Mirkin under his supervision in 2018, and it was named ParGNFS, and the algorithm performs parsimonious generalization of fuzzy leaf set, and the output of this method will be the set of head subjects, and the penalty function that we will have for as objective function of this algorithm to minimize is shown here. So we have different values of penalties for gap, for offshoot, and we have penalty equal to 1 for each head subject. So we can directly apply this algorithm to get generalizations for user segment profiles, and after that use them for targeting. And you can see here very interesting examples. I took here very small user profiles, and for the first example where you see initial segments were cloud computing, web development, internet for beginners, IT and internet support, social networking, we can just generalize all of this to the internet. And the second example is also quite interesting. We see here men's jewelry and watches, men's business wear, men's casual wear, men's auto wear. We can just generalize all of these to men's fashion. And the similar for the first sorry, for the third example, here we obtained two head subjects. And at the next step of our algorithm, we will use this to define corresponding set of advertising campaigns appropriate for these users. So the three-step method will include the following. So initially, we still have to compute membership values for interest segments for user by some classifier. This is step. This step is always present for each approach in programmatic. We should define user interests to perform all next steps. Second step is performing generalization of those sets and obtaining head segments. This is the most important part of our method. And the last step is to obtain the list of appropriate advertising campaigns for each user that will correspond not to initial user segments, but to high-ranked segments that were obtained in the step 2. And this list will be the set of appropriate campaigns. And we conducted experiments in the company where I worked those times in Mathematica, and we took 3 real advertising campaigns, and we compared first of all conventional programmatic targeting. The second approach just decreasing thresholds, and the new invented approach that is based on lifting of these user segments. And the metrics to compare were first was number of advertising impressions. So this is the core metric to calculate the audience size, of course, just to define to what number of users we can show these advertising campaigns. And the second is the quality of this audience. Quality can be measured by a number of ways, but here we will use just so-called CTR, click-through rate. This is the ratio of a number of clicks, that is B in the ratio, and A the number of impressions for each advertisement. And here you can see the results for the first advertising campaign. Was devoted to software for parental control for children. I emphasize here the duration of this advertising campaign, because duration sometimes is very important, since in some cases we have now enough information about users and about the some audience parameters before the campaign starts. So when campaign starts, we sequentially improve the quality of targeting. And here you can see also the IAB segments selected for this campaign. For the campaigns, usually they assigned manually by some account manager or the person who is responsible to select the audience that is appropriate for the company who buys the advertisement. And as you see, initially we have quite a restricted amount of impressions. After using CASE and LUSP approaches, both of them were managed to significantly increase the number of impressions. But for if we will take a look at the quality of this audience, of this extended audience, we see that LUSP method that is based on extending audience by generalization of user profiles. This method has way better quality of extended audience. This is clearly clear if we take a look at the CTR obtained for the companies. Of course, the initial CTR was a bit better, but for straightforward method CASE, we obtained way lower CTR. That means that the quality of audience in this case was not so good. And for two more advertising campaigns, we see approximately the same results. The second campaign was devoted to frame houses for villages, and this company had very restricted duration. And here we again see the quality of LUSP method is the same as it was initially, and we managed to significantly extend the number of advertising impressions, and as a consequence, of course, we have more clicks. And for a third advertising campaign that was devoted to mortgage in a major Russian bank, we see pretty the same result. Of course, CTR for LUSP method was a bit lower than it was for initial audience, but nevertheless, we were able to significantly improve the amount of impressions. That was a very good result here. So these results prove that this approach works indeed. And we can conclude that the amount of the increased amount of the number of clicks by LUSP was 74%. So the maximum amount of clicks for just lessening of belongingness thresholds was just 44%. So that proves that the quality of audience that we get if we use generalized user segments instead of just lessening the belongingness values. So this way works way better. So for the future plans, I would like to emphasize further expanding of tested advertising campaigns, because there are many different campaigns with different duration and different user segments assigned. So we can have an opportunity to check how this method works for very long campaigns. Here we already proved that it works on quite short campaigns where we have restricted duration, where we have restricted amount of further contacts with user expressed in impressions, and compare this LUSP method with audience proximity lookalike methods. Lookalike is a family of the methods where we, instead of modifying somehow targeting procedures, we just either buy a new audience somewhere. This can be inappropriate for small companies because it's technically impossible sometimes, but for some medium-sized companies, this is quite common way where the companies share each other audience, and they also try to find similar audience, say by matching user profiles, by finding some intersections between user profiles and stuff like that. This is very wide family of different methods. And the second is sorry, and the third is developing a strategy for parameters fitting, because currently we just used fixed values of our parameters of this algorithm, and of course we can think about how can we make the selection maybe automatic or adjustable during the work of the this algorithm. That would be great. Yeah, thank you for your attention. Thank you. Mm-hmm.
What are impressions? How are they measured?
Mm-hmm. Impressions is the event when some user sees the advertisement. This is can be either the banner, or that can be some video, for example. And the important issue here is how to measure that, because different companies have a different approach to measure these contacts. For example, some companies just use special JavaScript events to measure that. So if more than half of picture of ads is visible to user. I mean, it's it appeared on the visible part of the screen. This can be impression. For other companies, they use just loading of these ads. In our case, we tried to follow the most strict definition of impression. The first one that I described, more than half of picture of the advertisement should be visible at the user's screen. And in that case, that will be impression.
Thank you very much. Just a long eye contact with the advertisement.
This is usually most commonly this is undefined by but it some companies use and we also follow this. It should be at least one second. So
Really?
if at yes.
Well, thank you. And could you please explain? Each advertisement has a set of keywords or tags. How to define its?
Yeah, thank you for this question. So yeah, from the advertisement side, most commonly these segments are defined manually by special people in the company, either on buyer side or at the agency side, and they are fixed. And for example, if we would like to, if we have advertising campaign about Volvo cars, we can choose the segments: Volvo car owner, people who are going to buy a car. We can also specify some demographic segments such as age or gender or some geolocation, and these things are defined manually in most cases.
Thank you very much. Any more questions? Online participants, no questions?
I have a question.
Please.
Dmitry, I have this question. This approach, is it possible to apply this approach to building recommender systems?
Yeah, this is very interesting question. So yes, I think this is possible because there are many different kinds of recommender system. Some of them are based on different engines such as collaborative filtering. Other use more interpretable techniques such as matching between some things that are similar to what we have in internet advertising. From my experience, I can definitely say that in some recommender systems, companies deal with similar content taxonomies, very similar to what we have in internet advertising. And for these recommender systems, we will solve pretty the same problem, where we have restrict, for example, some set of content and users. So, and the issue will be just to set the to choose appropriate content for some users, and we will solve the same problem. From my personal experience, I can tell about working in my previous company where we worked with very large content taxonomy that is at least twice larger than IAB taxonomy. The company had its own content taxonomy that contained 6 or maybe even 7 layers of different segments. So in that case, I think this is a good input data to develop here this this recommender engine based on this generalization in taxonomies.
Let's start. We consider variation inequality problem. On the slide, you can see this formulation. In the unconstrained setting, this problem is written is quite similar. We just need to find some point z star such that operator f in this point z star is equal to 0. In the first glance, this problem looks like quite strange because we don't know what is the operator, but to emphasize that this problem is quite general, we can consider some particular examples when this problem arises. For example, the first typical and very popular example is the minimization problem, when we try to minimize some function f, and if we put the operator in the variation inequality as the gradient of this function, we need to solve the problem of the search of the stationary point of the function. In convex setting, it is equal to the minimization, and in non-convex, just to search of the stationary point, but it's enough because this is the best guarantees what we can do in theory for non-convex setting. Another example is saddle point problem. Here we have not only minimization, but here the typo, minimization and maximization here. And here we use the operator f, and we take the gradient on variable x, the variable in what we minimize, and anti-gradient on variable y, the variable in what we maximize. And it's easy to show that we try to find the stationary point not only on the gradient x, but only in gradient y also. And in the convex concave setting, this is equal to the to find the saddle point problem. Also, here we can consider the fixed point problem. Here we have operator tau, capital tau, and we need to find some point z star such that tau in the z points z star is equal to tau. This is stationary point, fixed point of the operator. And here we can put f, the operator in the variation inequality, as z minus tau z. And we find with this operator the fixed point of the operator tau. Okay, in our research, we consider finite-sum case of the operator f, and we assume that the operator f is some kind of average sum of other operators fi. This setting is common to machine learning because typically, for example, empirical risk minimization is the sum of losses of our model in different data points. We have weights of the model Z and model F. We input the some point xy and weight Z to the model, and compare the output of the model with the real label yi, and penalize the difference between them. If we speak about saddle point problems in terms of machine learning, here we can give example of adversarial training. It is close to the original empirical risk minimization on the slide, but here we add some kind of adversarial noise delta I to each of the sample. Using this noise, we make some kind of make our training process more robust, because this noise also trained during the process of training of the weights of the model, and these weights make our dataset more adversarial to our training, and that's why we can avoid the process of overtraining and other bad examples. And it's also good to avoid to save against adversarial attacks if we use our model with delta noise. Okay, this is a practical example when minimization and saddle point problems arises in machine learning. Next, we give some assumptions on our operators, the general operator F and the summons Fi, to make our theoretical analysis. Here we give two assumptions, co-coercivity and strong monotonicity. Co-coercivity is some kind of assumptions like Lipschitzness of convex function. And for minimization problems, a Lipschitzness of the gradient of convex function and L co-coercivity is equivalent. But for saddle point problems, the Lipschitzness of the gradients and L co-coercivity is not the same, and L co-coercivity is more restricted, but also general. And one more assumption is strong monotonicity of the general operator F. For minimization problems and for the saddle point problems, it is equivalent to strong convexity of minimization problem, of target function of the minimization problem, and strong convexity, strong concavity of the target function in the saddle point problem. Okay. If we speak about stochastic methods for our problem, for our finite-sum problem, okay, the main problem of the finite-sum, it is typical to machine learning. It is too expensive to compute the full gradient. That's why we just compute some gradients on small batches, and using these batches, organize the process of training. And here we can, on this slide, you can see the typical form of the stochastic gradient method. We have some kind of operator Vk. It can be, for example, in SGD, we use some, for example, we can choose randomly one of the summand and use it as a gradient instead of the full gradient. This is just typical most common SGD version of saddle point problems. Is not SGD, but stochastic gradient descent ascent, because we not only descend to the optimum, but also ascend to the maximization value. There are another version of methods for finite-sum problems, for example, SVRG methods. In SVRG methods, we don't only compute the value of operator Fy in current point Zk, but also make this correction. This correction here, correction in point Wk. Wk is some kind of reference point, which we are updated very rarely. For example, in 1 times per a big number of iterations. And in this point Wk, we compute the full operator or full gradient. But because we updated it very rarely, this full gradient is also computes very rarely. And we made some kind of correction, and this using fi in point vk and the full operator in point vk. And near the solution, this vk operator for SVRG is a good approximation for the real gradient, for the real stochastic, for the real deterministic gradient, for the real deterministic operator. Another approach is the SARA approach, the main approach of our research. It is close to the SVRG. Ideas is common, but here we updated this operator vk on the flight. We don't compute, we don't use the reference point like in SVRG, but modify this vk using current point and previous point. And experiments of the shows that SARA is more robust and has smoother trajectory of the convergence than SVRG. Okay, and here we provide the full algorithms of the SARA for stochastic coercive variation inequalities. There are two loops. The main loops on variable s and the inner loop on variable k. In the main loop, we need to update the full operator as this v operator, v0 operator. Then on the inner loops, we made SARA updates. And here you can see the convergence of the algorithm. And theorems says that under our assumptions, we can guarantee that one epoch, one outer iteration, our main iteration of our algorithm, can guarantee the norm of the operator or norm of the gradients became smaller, two times smaller. And also we provide a corollary with the complexity, oracle complexity of our algorithms. You can also see it on the slide. Then I will show you experiments. We provide experiments on the small bilinear problem. This is a saddle point problems. On the slide, you can see the how we can generate the different parameters of these problems. And we use SVRG and SGD from the previous slides as the competitors of in our experiments. And in plots, you see how SVRG, SGD, and SARA works for this toy bilinear problem. And you can see that our method outperforms the competitors from the previous papers. Okay, thank you. That's all.
Еще разок. Thank you for your presentation.
Thank you.
Any questions?
Huh?
Have you questions? Please.
Thank you for your presentation. I wanted to ask. Excuse me. No.
I hear, yes.
Yes. I wanted to ask how your method compares to the Nesterov method, or is it part of one of the? How does it compare to yours?
Here, the main problem is that variation inequalities is more general problem than minimization. Nesterov's method is also works for minimization problem, but for variation inequalities and saddle point problems, it can be proved that there is no Nesterov acceleration. We can accelerate theoretically these problems. That's why in theory Nesterov's methods works the same as original methods for saddle point problems, for example, methods from the slide. And typically in practice, the situation is the same.
All right,
or
thank you.
Even worse.
Thank you very much again. I invite the next speaker.
Okay, thank you.
Neumann. Are you here?
Hello, I'm here.
You're welcome to start your talk.
Thank you. You all see my screen?
Yes.
Okay, good. So I developed a parallel linear active set method. My name is Doug Neiman. I'm from Siemens Institute of Technology. The goal was to find a speedy closed-form method for minimizing a convex function under linear inequality constraints. And we found one given a convex minimization method for linear equality constraints. That is closed form. So what do I mean by closed form? It's just an algorithm that will solve it in a finite number of steps. An algorithm that will find the minimal point of the convex function in a finite number of steps, which means not an answer with an epsilon ball and not an asymptotic algorithm. There are many closed form linear equality convex minimization methods. So relying on the existence of one is not a waste of time. For example, the common projection function onto an affine space. An affine space is a set of linear equalities, and and we solve that in O of n cubed operations. More broadly, any function that we can solve in that we can find the minimal point for in an unconstrained space is also something that we can solve for a linear equality constrained space by use of a change of variables. So there are a lot of them, and that's handy because we rely on the existence of such a method. We call that method that solves the minimal point for a convex function over linear equality constraints. We'll just call that our black box method because it doesn't matter how it works. We just need it to work. And if our black box method isn't closed form, then our algorithm still works. It's just not closed form, but it's still a nice algorithm, and it has some really nice multi-threading properties, as you'll see. For inequality constraints, are there any questions so far? Okay. For inequality constraints, there is some existing work with generating closed form algorithms. There's a projection method for Hilbert spaces, which has exponential complexity, and when multi-threaded, it has cubic complexity, and that's as a function of the number of constraints. There are closed form solutions for some convex quadratic objective functions over linear inequality constraints in Euclidean space. And the list goes on. There's a specific Euclidean projection function also from which we build our method, but we managed to make a number of improvements over their method, which I'll talk about toward the end. We're using n for the dimension. We're working in a Hilbert space. N is the dimensionality of the Hilbert space, and our convex objective function we'll call f. We use c less than or equal to denote our R inequality constraints. And if later R comes up and you forget, hey, what was R supposed to be again? Just ask. It's the number of inequality constraints. We use c equals for the number for the corresponding equality constraint. So we take an inequality constraint and swap out the inequality sign with an equal sign, and then we have an equality constraint. And we're going to come back to that also. We use P to denote the feasible space for C less than equal for the inequality constraints. Okay. A few definitions that are necessary in order for the algorithm to make sense. We call A an affine space of P if it's the feasible space of some of our linear equality constraints, and a plane of P if it's a feasible space of a single linear equality constraint. Naturally, every affine space of P is going to be the intersection of a number of planes of P, and that's important. We'll come back to that. For an affine space A of P, for every affine space, we also build a cone. And just because every affine space is the intersection, every affine space is the intersection of planes. So if we swap those planes out with half spaces, and take the intersection of those half spaces, we get the cone. So affine space equality constraints, the cone is the corresponding inequality constraints. For example, if an affine space is the intersection of the blue line and the green line, then the cone of that affine space is the intersection of the blue half space and the green half space. Hopefully that's pretty straightforward and makes sense. If anybody's confused about that, it's going to come up again, so ask now. Okay, good, moving on. One last definition, we call it an immediate superspace. So if a affine space is the intersection of M planes, then the immediate superspace would be the intersection of any m-1 of those planes. And for example, if we'll use this affine space this time, so the intersection of the green line and the purple line is an affine space, so the immediate superspaces are just the purple line or just the green line, because we take away one of those constraints and whatever's in the intersection of the remaining equality constraints is the immediate superspace. The immediate superspace of the blue line is just the Hilbert space, and and there are no immediate superspaces of the Hilbert space. Questions? So now we have two slides over which I present the closed form method. In the first, we find the closed form minimal point over one of our cones. So it's recursive to find the closed form minimal point over a cone of an affine space A. We look at all the immediate superspaces of A and find the minimal points over their cones. If the minimal points over any of their cones is in the cone in question, is in the cone of A, then that is the minimal point of the cone of A. And that's kind of immediate because the super cones contain, so this PB here contains PA. If it's the cone of an immediate superspace, then it contains the cone of A. So that's obvious. What we proved in the paper was that if it's not any of these, then it's going to be the minimal point over the cone of A is equal to the minimal point over the affine space A, and that we compute with the black box function. So it's a closed form expression for any cone, any polyhedral cone more generally, and specifically any cone of P. Once we are able to compute the closed form of, are there any questions about this slide? Okay. So once we're able to compute the minimal point over the cone of A, we then just look through all the cones, and we can do this with a certain order. We can look through all the cones and find the one that has the property that the optimal point over the cone is equal to the optimal point over the affine space, which we computed here. And the cone that has that property, if the minimal point is also in P, then we got it. Then that minimal point is the minimal point of P. The argument of F over P is equal to the argument of F over that affine space. So that's the closed form. Questions? Okay, good. There's a little bit more. Okay, so we can organize that into an algorithm rather, right? If we just choose, you know, the vertices of our polyhedron, if we just choose sort of the points at the tips of P, and then it's not so organized and it's going to be a mess. But if there's a little bit of organization here. So we'll first go over all, and also rather than present here the optimization or the minimization method that's in the paper, I kind of simplified it to just solving the projection problem here in R2 to make it easier on your eyes. But this method mirrors line for line the optimization method in the paper, which is for a generic Hilbert space and a convex function. But here we're just solving a projection onto our example here. If you don't know what a projection function is, say, hey, Dov, I don't know what a projection function is now. And I'll be like, okay, and I'll tell you, and it's easy. Good. We all know what projection functions are. Please stop me at any time if you decide to raise your hand and say you don't. Okay, so we just go over first all the affine spaces of codimension 0. So it's the intersection of 0 planes. Again, that's our Hilbert space. And then we go over all the affine spaces of codimension 1. So those are planes. And then codimension 2, the intersection of any 2 planes, and the intersection of any 3 planes, and so on. So that's just these 2 loops here. And the nice thing about this inner loop is that, of course, looking at one affine space is completely independent of looking at another affine space. So those can all be done in parallel, which is very nice. Once we have selected an affine space of, let's say, codimension I, so we look at all of the optimal points over the immediate superspaces of that, or over the cones of the immediate superspaces of that affine space. And the nice thing is that we already computed all of those optimal points when we were looking at I-1. So we know what this little pi b here. Pi b is the projection onto the cone of B. So if there is a pi b that's in the cone of A, then we now know the optimal point over the cone of A, and we never need to call the black box method. And this is the strength of this of the algorithm that we developed. We can find the optimal point over a cone without calling the black box method. And as the number of inequalities increases, I'll come back to that later. Sorry. Okay. And if we don't have any immediate superspaces that the projection onto their cones is in the cone that we're currently looking at, then we call the black box method by computing the projection onto the affine space and check if that projection is in P. If it is, we're done, yay, and return that point as the projection onto P. If we go through all the affine spaces and we never found that, then we just return an empty set because the argument of our polyhedron is in fact empty. There is no minimum argument. And that's either because the P is empty or because there's it's unbounded and there's just no minimum on that set. In the paper, we also guarantee that such an affine space that has this property, in the paper, we guarantee that such an affine space that has this property here exists. So it's there and we'll find it. That's the algorithms. Are there any questions on what I wrote here that I'm calling? Oh, thank you so much for answering. No. Okay, great. So the complexity, so for the projection sort of subproblem, when the number of inequality constraints is much greater than n, our complexity is O of r to the n times Rn plus n cubed, which is polynomial as a function of the number of inequality constraints, which is exciting, unless, of course, your dimensionality is big, and then being polynomial is still a mess. But here's the neat thing. We can actually run the whole thing in parallel, at least in parallel as a function of the number of inequality constraints. And then the complexity is O of n to the fourth, which, and I'll remind you all, n is the number of dimensions, over r to the n plus 1 processors. So that can be neat sometimes, I think. For more generic complexity, when we're not looking at just the projection problem, so it's, or when the number of dimensions, like it's a Hilbert space, if there's an infinite number of dimensions, or there are just a lot more dimensions than the number of constraints. So then this statement here is our complexity, where I use these brackets to indicate the complexity of doing whatever's inside of them. So we have, right, whatever's less, r to the n or 2 to the r, which means that if n is huge, we're looking at 2 to the r, which isn't a function of n. And if r is huge, then we're looking at r to the n, which is a polynomial. And then it's just the number of constraints times however long it takes to do inner product, plus however long it takes to call our black box method. If we have a bunch of processors, either right, whatever's less, 2 to the r or r to the n processors, then it becomes min whatever's less n or r times the complexity of computing the inner product plus the complexity of computing the black box method. And with regards to it being closed form, so obviously if argmin f over a is in closed form, then our complexity isn't. Also, if we're in a Hilbert space, so usually computing inner product in Hilbert spaces can have an epsilon component in the complexity, and then it's not closed form either in the complexity of computing inner product, because it's infinite dimensional space, and that's integrals and whatnot. So that's the complexity. This improvements over the progenitor method. So the first is that the progenitor method looks at all the affine spaces and calls the black box method for every single affine space. So what we found numerically, and I started to say this earlier, but then changed subjects, what we found numerically is that as the number of constraints increases, the condition on line 2 is met, sorry, the condition on line 3 is met more and more, and we don't have to call the black box method. So as the number of constraints increases, or also as the number of dimensions increases, we call the black box method less, approaching 0, as a percentage of the number of constraints or dimensions that we're looking at. So that's a big win. Also, the previous method reviews all the affine spaces and then finds sort of the best amongst those, or the minimum of the results from calling the black box method on all of those. And our method stops when we get to the right answer. We recognize it and we're done. So that's nice. Okay, those are the advantages of our method over the progenitor method. Thank you. Questions?
Can I? Okay. You speak about the algorithm and you have a starting point, I think, y belong to it or something like that, in the nicest you had in your presentation. Yes, in the first line you have a point y belong to H, Hilbert space, I think. My question is about the y, exactly the point of y. Is this point affected on your algorithm, or we can choose this y arbitrary or something like that?
Thank you so much for catching that. It's unclear, and I appreciate you pointing it out. So there is no, for an arbitrary function, objective function, for an arbitrary objective function that we're trying to minimize, there is no point y. It's not an iterative algorithm that starts with y and like y moves closer to the final destination with every iteration. And the y here is just the point being projected. because I'm specifically looking at a projection function. So for projecting a point onto a feasible space, so right, this is the feasible space, and this is the point y that's being projected. So we're looking for the closest point in the feasible space to y. Hopefully that answers your question.
Okay, thank you.
Thank you.
Yes, I'm here. Yes, I'm here. Okay. Okay. Hello, everyone. Okay. And I would. So my name is Boris Kovalerchuk, and I will talk about interpretable machine learning for self-service high-risk decision-making at its joint talk with my former student, Charles Rickaiden. Okay. First of all, I want to congratulate Boris Grigorovich Mirkin with his 80 years old. We met a long time ago in 1971 or before in Akademgorodok. And what he did that time, he actually reviewed my master's thesis at the Maths Department of Novosibirsk University. Much later, I reviewed his doctoral dissertation. And of course, we talked about all these scientific works for many years. And I just want to mention that all his good work was reported in the proceedings, but one problem which he solved in 2004 was not there. I call it Mirkin's stream problem, and I would like you to show this, and you will see how elegant his solution was. Should it be in the Springer volume 2? It's the question that can be discussed. Okay, let me show you this, his solution.
Yes, I remember it.
Okay, so hopefully everybody see that he really solved the problem. Okay, now we go to the technical part. So I will talk about dynamic scaffolding coordinates, which we developed, and how they can solve the problem, which I just outlined at the first slide. So first of all, machine learning more and more used for high-risk decisions like car driving, cancer diagnostics, and unfortunately, many of these models are black boxes for end users, and obviously they are not human interpretable, and for high-risk scenario, it is unacceptable. So the main goal in very active research now, how to make these models more interpretable. And this is one of the topics of my presentation. Let me give you one notable example. High-risk patients are admitted to the hospital and low-risk patients are treated as outpatients. The rule-based model has shown that having asthma correlated to low-risk patients. This byproduct of asthma treatment reducing pneumonia risk. This rule was intelligible, allowing to recognize and remove this dangerous rule. But of course, if it would be neural network or deep neural network, obviously it would be impossible. And obviously, this is a risky business. So now the first problem and objective is really to advance the area of black boxes, make them at least gray or ideally transparent boxes. So we specifically talk about two visually interpretable self-service models to expand field of graphics-based machine learning. I would like to emphasize the word self-service models because the making models interpretable assumes that user will agree with it. So it is not only question how nice and how many formulas we will write down and how many theorems we prove. User should agree with this. And ideally, if the user will be involved or actually create model, trust will come with this. Not necessary all the time, but it can have much more chances. Another problem is reliability of machine learning models in high-risk scenarios. Unfortunately, like I will show later on, many evaluations of machine learning models are exaggerated in their accuracy, which is again unacceptable for applications with the high-risk cost. And again, we use visual knowledge discovery approach for the estimation and finding worst-case validation splits to discover best algorithms or models for the worst data. It's basically a concept of Shannon function. Okay, now a few words why visuals. You can see here the long list of scientists who claim that visuals play the most important role in their discoveries, and Albert Einstein was very clear on this too. So, but the problem is, how can we do visual discovery in n-dimensional data, because we live in three-dimensional world and we really do not see high-dimensional data to do this. So the current approach is mostly based on two things: lossy dimension reduction, like principal component analysis, multidimensional scaling, and a whole bunch of other methods, or splitting ND data to sets of low dimensionals. The first one obviously lose some information, and the second one destroy integrity of ND data. So our first approach is that we really need to go out of that approach where we try to represent n-dimensional points as a two-dimensional, three-dimensional point, but actually represent as a graph in 2D, not as a point. This is a way how we can preserve ND information. I will show a few examples. Okay, this is on the left example with parallel coordinates, which were developed over 100 years ago and completely forgotten before Albert Inselberg at IBM rediscovered them. So we have a four-dimensional point 8479, and each coordinate are located vertically, and you connect those points on each coordinate as a polyline, and this polyline is a graph, obviously one-to-one mapped with the four-dimensional point, and obviously it can be done for any dimensions. On the right is a shifted paired coordinates, which we developed. So it does not exist for 100 years, but it's quite simple. So what we have two Cartesian coordinates shifted one after another. So the first pair values 8, 4 in one, 7, 9 in another pair of coordinates, and we just connect them using the arrow. Again, very simple graph. If you compare these two graphs, you can see that parallel coordinates require drawing 4 points and 3 lines, but shifted pair only 1 line and 2 points, and both of them are lossless, representing fully four-dimensional and obviously generalizable to larger dimension. Okay, then we have a Johnson-Lindenstrauss lemma. They proved it in 1984, and in 2000, several versions of this theorem appeared with other estimates. But basically, what this theorem tells us, it tells us a fundamental limit of lossless visualization of ND data in 2D. Simply means that the errors which we get in lower dimensions will be very significant. I try to skip many details, but basically conclusion is very obvious. We simply don't have enough neighbors with equal distances in smaller dimension space to represent fully ND data. It is very illuminated in binary cubed n-dimensional, where we have over 1,000 nodes, but in 2 dimensions in square, we have only 4 nodes. Okay, what we actually did in this work, developed dynamic scaffold coordinates, visualize ND data in these coordinates losslessly, and in class, improve class separation based on it, and again, found the worst case data split using this technique. So the main concept here is a general line coordinates, which I introduced in 2014, and in detail, it's presented in the book published by Springer in 2018. So the main idea I already outlined, it's to use graphs instead of points to represent ND data. And for several types, we already did in our team this work, and this particular work with one particular type of general line coordinates. Okay, now I just will illustrate them visually. So on the left, you can see parallel coordinates, which I already explained. In the middle, you can see modified parallel coordinates, where we allow the lines be not only parallel, but in different directions. Then we can allow all coordinates be online, in single line. We can allow them to be on the edges of n-gons, circles, be curvilinear. Basically, there are infinite number of possible general line coordinates, and all of them allow lossless representation of ND data, in contrast with traditional orthogonal Cartesian coordinates, which only limited by 3 dimensions. So the fundamental idea that when Descartes created his coordinates over 400 years ago, the idea was to describe the physical world, which perfectly matched the idea of orthogonal 3-dimensional coordinates. But for data science, we really need to go to this type of coordinates because they allow to represent multidimensional data. I call this sometimes as ND glasses. Okay, we have several statements mathematical about general line coordinates. Basically, the main of them is that similarity of graphs can be matched one-to-one with the distances between ND points. Okay, now we talk about the hurdles that we have here. First of all, multiplicity of methods of visualizations, and this lead to the effect that the same data with different methods visualize it very differently. And you can see here this example. Moreover, it's the same data, just order of attributes dramatically change visualization. It's not only hurdle, but it's also advantage, because it allows to find a visualization where classes are visually well separated and obviously convincing the user that he or she can trust it. Okay, now another challenge. We have here 4 non-overlapping 3-dimensional subsets, but they do not overlap in 3 dimensions. And there are multiple examples similar in n-dimensional data. But here in visualization in 2D, while it's lossless, they are heavily overlap and obviously not very much useful for convincing the user. So we want to resolve this problem. Okay, let me need to move to another slide. Okay. And for whatever reason, it's frozen and does not allow me to move my slides. Oh my goodness. Finally, it moved. Okay, now I need to explain how the dynamic scaffolding coordinates, which we abbreviate as a DSC, are designed. So we first put data to parallel coordinates, then we change directions of the parallel coordinates, and then we find vectors shown as a yellow vectors which go to each of those points in the tilted parallel coordinates, and then we connect yellow vectors one after another, basically summing them up. And now you can see on the right how this very nonlinear transformation converted those data from parallel coordinates to DSC1, and you can see that separation of patterns and three classes of actually iris flowers much more visible. Okay, this is another version of dynamic scaffolding coordinates based not on parallel coordinates, but shifted paired coordinates. On the left, you can see this data represented in shifted paired coordinates. Then for each point represented in shifted paired coordinates, we again compute vectors going from the origin of respective coordinate system to those points, and then we sum up those vectors, omitting the first vector. And as a result, you can see on the right the result of this nonlinear transformation. And again, classes are separated, but not that good as we want. So next step is actually to scale attributes. So now we are not simply use equally scaled pairs of coordinates, but the second, third pairs are smaller. And now you can see that with this trick, we can have much better separation of classes, and moreover, very visible the area where they are overlapping. So this creates a basis to find the worst case validation data for algorithms. So now you can see that we want to deal with overlap reduction technique. We have several options which we actually implement. First one, it's building hyperblocks and analyze them using decision trees or any other existing good machine learning methods for better separation. Of course, using additional attributes like principal component analysis, using them in addition to the original attributes. Okay, and using now became popular T distributed stochastic neighbor embedding. Okay. Okay. So now we go to the next slide. It's a 10-minute challenge to keep it working. My goodness. It's a permanent challenge for me to It is frozen. Yes, I try. Okay, it looks now it's there. So now you can see two different overlaps of the data, and which we want to remove. And you can see that they have a different importance. One does not really impact classification, and another one impacted. So we need to be able to see this. Okay, so now I will show the technique. First of all, I need to introduce hyperblock concept. It's basically a generalization of the rectangle to n-dimensional space called n orthotop. And what we try to do, we built a decision tree and use the most informative attributes of the decision trees as fast coordinates which we will use in the data. So now you can see other data set with its decision tree, and now the result using the method which I described. When attribute we scaled, and we also can use decision tree guidance. And you can see areas of the worst cases are very visible to the end user for self-service decision. Okay, now it's the similar things for Wisconsin breast cancer data and decision trees. And again, this is a result of this data in our visualization method with scaling, and you can see that areas of the overlap become very clear. Okay, so now this is a combination with the principal component analysis. On the left, it's a standard principal components where you represent, in this case, 10-dimensional data as 2D points with two fast principal components. And the second one using our DSC tool, where it's quite better visible where the worst case overlap areas are located. And now this is an analysis with different machine learning algorithms, from decision trees to KNN, support vector machine, and so on tenfold cross-validation data on the same data which I shown you before. And you can see average of the tenfold cross-validation, the winner is support vector machine. But for the worst case, it's a random forest. And you see the difference is very dramatic between 97% and 61.9%. And multilinear perceptron was really terrible, from 89% to 23%. So for the risky tasks, it would be really not satisfiable to use SVM, which in the worst case just shown 38%. Similar for the cancer data, but different algorithm is a winner here. KNN for tenfold cross-validation, but naive bias for worst case. And obviously, cancer case, it's definitely high-risk task. And now I can show how we try to work with mnist handwritten digits, which total data set contains 60,000 images. On the left, it's more a standard TSNA visualization, and on the right with our additions. Basically, TSNA represent them as a single point, and we show as a graphs. Of course, it's need to be zoomed multiple times to see details, so it provides more information for analysis. So there are several other methods proposed in the literature. Most popular today, it's LIME, Local Interpretable Model Agnostic Explanations, developed at the University of Washington. What they do, they use linear machine learning models to interpolate relations between input and output at the local level. And assumption is that linear models are always interpretable. We actually challenge this assumption because for heterogeneous data like medicine, where we have temperature, blood pressure, it is not so obvious, and we call them quasi-explainable. But in contrast, hyperblocks as a generalization of decision trees are 100% interpretable. So Charles obviously developed all this software, and with his skills, he was just hired by machine learning group at Amazon. And in conclusion, as you can see, those new visualization methods are lossless and allow do visualization, classification, and analysis of data. And hyperblocks have advantages that they build more complex models than decision trees. And feature engineering, like adding additional features I demonstrated, is another way to improve the situation. And again, worst case validation is doable in this visual way, and convincing the user to trust or not to trust particular method. Okay, future work obviously is going to more complex, larger data sets and with more efficient methods. This is a few illustrations when we basically only visualize hyperblock centers, similar to popular clustering approaches, which Boris Mirkin worked for years. And on the right, another options. That's basically it in my talk. Yes, a good question. Yes, we have, of course, those algorithms too. And we actually compare it, how competitive automatic algorithm with the human. And in some cases, humans were actually better. But definitely, you're right. And we used, one of the ideas was, of course, because it's a two-dimensional image, we can scan this image and finding least pure areas. In contrast to multidimensional space, it's a quite easy way. Another option was to use a support vector machine, the support vectors, and explore areas close to them, because they're supposed to be close to the border, so guiding a human and automatic algorithm. Theoretically, yes. So, but the problem is that for each algorithm, the area is not the same. So if you believe, so for example, if we decide that support vector machine is the best one for, say, some other reasons than pure accuracy, then of course we can pick up those areas where it did not work well and use, say, KNN in those areas. Yeah, that's good. Mm-hmm. Sure. Yeah, sure, no problem. Basically, you need to ask Boris Grigorovich.
I don't have them. I have noticed pictures. So Boris, it's really quite beautiful pictures. I've never seen them.
Okay. Okay, thank you.
Which are alternatives that are the best alternative for at least one person in a society, and bets that not alternative that everybody hates, but alternative that everybody do not put as on a top of preference profile, preference order. So we have goods which are best alternative for at least one, and bets which are not best alternative. So, and I studied structured preferences. So we have structured preference space, structured alternative space, and as a consequence, structured preference space. So the most influential example is single peak preferences. So we have a line where we have alternatives and agents ideal points, and the further alternative is from ideal points, the worse it is. So we have different types of single peak preferences. So general single peak preferences, we have a line and all alternatives on one line. We have error single peak preferences, so we have single peakedness on each triple. We have a single peaked on a circle, so the same idea. So we have circle topology, and we have so agents, ideal points, and alternatives on the same circle, and fishbone domains where we mix single peakedness and single deepness. So formally, we can introduce single peaked preferences as the following. So a domain of single peak preferences is defined by an axis. So we have a linear order over X. This is an axis. A preference profile pi is single peaked with respect to an axis A if for each agent the upper counter sets are connected according to this axis, and this. So we do not define distance between alternatives. We do not define distance between agent and alternatives. So we have the following property: their ideal points, and we can order all alternatives to the left and order all alternatives to the right. And we cannot compare alternatives from the left and from the right from ideal points. And this property we have connected upper counter sets are very useful in computer science. So we have matrices with consecutive ones, and we can utilize this property in algorithms, and many problems within single peaked preferences becomes tractable whenever in general some problems are NP-hard. So we can imagine any
preference model. So we can think that a society have, in some sense, people are clustered. So we have not all possible preference order in society, but some subset of preference orders, and this subset is called domain, and we can imagine a variety of domains, and we need to think that these domains have some properties, and we want to restrict our domains to domains with good interpretable properties, and these are these properties. So firstly, we want to have Condorcet domains. So within this domain, every profile composed from preferences from this domain has a cyclic majority relation. And in economics, political science, computer science, first of all, we study Condorcet domains. And these domains are so leads to transitive majority relation, have graphical representation, simplifies computationally hard problems, and so on. And within these domains are also very different, and not all of them are have good interpretation. So we have properties within Condorcet domain. So Condorcet domain D is connected if every two orders from the domain can be obtained from each other by a sequence of transposition of neighboring alternatives, such that the resulting order belongs to the domain at each step. So this means that we do not require big shifts, big changes in preferences. So you can always find something close to your current preference order. So maybe within only one swap of preferences. So a Condorcet domain has maximal width if it contains a pair of completely reverse linear orders. So we allow diversity, we allow really different opinions in our society. Condorcet domain D is minimally rich if for each alternative there is an order from the domain such that this order has alternative X as a top alternative. So minimally richness reflects property that all alternatives are good, that for each alternative there is an agent, there is a preference order such that this alternative is the top alternative. And in my paper I want to weaken this property to weak minimal richness. So this alternative, each alternative is either top or bottom alternative in at least one preference order. So we have, if we have top alternative, so it is good alternative. If we have bottom alternative, it is in some sense bad. And what we have? We have classical characterization of single peak domain. So each single peak domain is connected and minimally rich Condorcet domain with maximal width. So, and we have if and only if, so it is really characterization of single peak domain. And if we weaken minimally richness to weak minimally richness, we get the class of GF domains. So the definition would be here. So it is the following structure. We have a linear ordering of alternatives, A1, AM, and a subset A such that if a triple, so for each triple of alternatives, AI, AJ, AK, if the median of this number belongs to this set, so AJ belongs to set A, then this triple is single dipped is the median. So is single picked if the median belongs to set x minus a, to then this triple is single dipped. So we can mix single pickedness and single dippedness. And so from first view it is strange, so we cannot interpret this definition, what the meaning of this preference is, but the following proposition introduce a very good picture. So single picked on a circle, so we have a circle with alternatives, with ideal points, with the same meaning of single pickedness. And what is interesting, GF domain is a subset of a Spock domain, so of single pick on a circle domain. So single pick on a circle domain is not Condorcet domain. So single picked on a circle domain is very big domain. It contains cycles, so the majority relation can be cyclic. And GF domain is the biggest Condorcet domain within single picked on a circle domain. And we can introduce the following picture, so it's the main picture of my talk. So we have a circle and we partition all alternatives on inside alternatives and outside alternatives, so goods and bads. And what is the meaning of this inside and outside alternatives? So they have two interpretations, at least two, so we can introduce many of them. So there is a lake and a beach which occupies an interval of lake coast. All agents take a rest on a beach. Alternatives are location of ice cream stands. Some of them are inside the beach, inside alternatives, other outside. Some outside alternatives are better than some inside alternatives for some agents, but there is no agent which has an outside alternative as the first choice. So all people have a rest on a beach, so within this dotted area, and they can think that the closures are better, and they can think they can compare outside alternatives, so the places outside the beach, but all of them think that inside beach there are better alternatives than outside the beach. So another interpretation is time or calendar circle. A 24-hour circle has common working hours interval. A video conference session should be proceed every day at exactly the same time slot, and all agents prefer to do it within working hours, but they can also compare outside alternatives. So if we have calendar, 365 days circle has a common school holidays interval. Students are going to have a trip, and all agents prefer to do it within their holidays, but can discuss other options. So I generalize standard preference model adding outside options. So preference model within inside options is introduced earlier. Single pick preferences, other examples, and if we add outside alternatives which are comparable but not the best, we can think about more general preference model, and this more general preference model can be transitive, so it is Condorcet domain and it is interpretable with this picture. So we can also think about some circle town, for example Moscow, and we can think about airport outside Moscow. So nearby Moscow, we can think that we should choose a point where we will have a new airport, and the same. So we have some inside alternatives, so some possible points and outside and so on. So that's all for today. Thank you for your attention. I'm brief, and that's all.
Thank you very much.
I would like to thank everybody who participated in so many ways that this conference became a reality. And I hope that we meet much more frequently, but for sure for 90 years celebration of Boris Mirkin. Please, Boris, remember you are responsible. Any questions, especially online?
Well, I suppose that I can be heard like this. Yes, just from what I understand, you presented a model, but there are no theorems at this point, or lemmas like result.
We have axiomatic justification. So this subset of preference solvers, this domain, is characterized by connectedness, by weak minimal richness, and maximal width.
All right, good, thank you.
So again, happy birthday to you, Boris. And thank you again, everybody. We are going to complete and to start our preparation for the next conference. Also, I use this opportunity to invite everybody who has not yet contributed to the book, because I believe you have a couple of hours to submit your contributions. Thank you again. Никто не хочет сказать? Okay, see you next time.